I request our students to please come forward for it. Anushka, Shriji, and Swarna. I also request to the audience, please do not clap up. जब बात मैं बोलूंगी कि मेरी शक्ल दिखा दे, उसके बाद कैमरे को बढ़ा करके ये स्क्रीन को फोकस कर दे, जब आपको आएगी आवाज तो नहीं आएगी, याद रखना। शांति यहाँ सही चल रहा है। मेरे Thank you, Anushka, Shrijit, and Swarna. As a mark of respect and also to formally welcome the guest and the dignitaries on the dais, I request Sneha and Shudeepa to please come forward and present the bouquets. Thank you, Sneha and Shudeepa. The Nobel Prize, a symbol of unparalleled excellence, has been honoring individuals and their groundbreaking contributions to its inception. Today, we gathered here to delve deeper into the remarkable discoveries and innovations that have shaped our understanding of the universe, the element that comprise it, and the intricate working of the human body. This event serves as a tribute to relentless pursuit of knowledge and tireless efforts of exceptional minds in their quest for the advancement of science and medicine. Rabindranath once said, "Find God, you must welcome everything." Indeed, nothing can be more reassuring and heartwarming than the affectionate word. Formally welcome us all here, I request our Director, Institute of Science, Professor Anil Tripathi, please deliver the welcome address.
Our Honorable Kulguru, Dr. Sir D.K. Shuklaji, distinguished speakers of the forenoon, Sir Pal Dikshit, Sanjay Singh, Sir Virendra Ghosh, our esteemed Dean, Faculty of Science, Sir SM Singh, distinguished professors, Narsingh University, Sir Yashwant Singh, Professor Rajiv Raman, Lalan Mishra, head of the departments, colleagues, and dear students. Today is 135th birth anniversary of an icon of science in India, Sir C.V. Raman. He has distinguished himself in many respects as he is an icon of self-confidence, self-esteem, excellence, deep excellence in knowledge, Indian traditions, and above all, he is a leader of science, eternal leader of Indian science in the country. A few years back, we decided that we should remember him, at least occasions which are important in his biography. And today happens to be his birth anniversary. Another very important thing is that at a very early age of 42 years, he was awarded Nobel Prize. When we look at the winners of the Nobel Prize these days, they are, except a few, barring a few, most of them are very old. He accomplished it with a great sense of confidence at a very early age. I'm very happy that we are continuing this tradition of offering him our tributes, our remembrance on this birthday, and by honoring him, we honor ourselves. And what can be a better way of offering our tributes to him by organizing talks the Nobel Prize winning works the recent year. Whenever we have this kind of talk, we always remember him, and he will continue to inspire the generations of young scientists, not so young scientists, to do good science with confidence for the sake of the country, for the self esteem of the country. Another reformer and a great leader of his time was founder of this university, Pandit Madan Mohan Malviya. And in fact, I think the teaching of physics started in this university by lectures by Sir C.V. Raman. And that is another point that we remember him so far. I'm very happy that today, like previous years, our Honorable Rector has graced the occasion. Despite his extremely busy schedule, he cannot say no to us, not only because of affection for us, but also because of the significance of this program. We very warmly welcome you, sir. Now, today we have, as I said, three very eminent speakers. We have Dr. Gopal Dikshit, who will be talking about femtosecond physics from IIT Mumbai. He gladly accepted our request. Professor H.N. Ghosh, Director NICE at Bhubaneswar, he also gladly accepted the request. And Dr. Sanjay Singh, who is keeping extremely busy, he also accepted our request, but of late he has some hesitation because he had some engagements, pressing engagements, and he wanted to deliver the talk online. But I said that I want my students to see Dr. Sanjay Singh in flesh and blood. Therefore, please be available physically. And he accepted, he consented my request. And Dr. Sanjay Singh arrived midnight, and he will be leaving around midnight because flights from Pune are not very convenient. I like to thank our organizer, Mr. Chelapati Rao and his team, who has organized this taken so much of effort to make this event a reality. And I, again, very warmly from the core of my heart, welcome all the students, faculty members who have assembled here. Because I would also like to mention that the Institute of Science is doing its best to contribute towards the eminence of the university in all spheres of the university. And it's a matter of great pride for us that this year, 4 of the faculty members from the Institute of Science were elected fellows of the National Academy of Sciences India. 2 of them were elected as associates for Indian Academy of Sciences. And the last one, INSA, 2 were elected as fellows. So this reflects the eminence of the Institute of Science, the kind of activities which are taking place. And I think the government of India and Ministry of Education should derive some sense of satisfaction. The kind of support which Ministry of Education has given to Banaras Hindu University as an institution of eminence, we are striving towards it, and we are trying to reach. And I think we are no less than of the ICERs which have been kind of accolades, publications, kind of recognitions which we are getting. With very meager resources in comparison to ICERs, we are doing extremely well. I'm very proud of it, and I hope all our faculty members, students, and research scholars will continue to strive for taking the excellence of this university to a global level. Once again, I welcome all of you for this very exciting program. Thank you very much.
Thank you so much, sir. Before we commence our intellectual journey, we are privileged to have with us today our esteemed rector, Professor V.K. Shukla. His valuable insights and leadership have been always instrumental in fostering an environment for academic excellence and innovations within this institution. I kindly request our rector, sir, please offer his blessing remarks, which will set a tone for these enlightening lectures.
Thank you, Archana. It gives me immense pleasure to extend warm welcome to the guest speakers of today's function. Pal Dikshit, IIT Mumbai, Mr. Ghosh, Director Nisar Bhubaneswar, Sanjay Singh, CEO Genova Biopharmaceuticals, Sarikya Tripathi, Director Institute of Science, Professor Singh, Dean Faculty of Science, senior professors, faculty members, dear students, ladies and gentlemen. At the outset, I'd like to congratulate Professor Tripathi for continuing this legacy of Sir C.V. Raman tutorial lecture. I happened to witness of them earlier. I was really impressed, and given the choice, I'll not like to miss it. I had a theater, so I just did a one case and left in between. I came here to join you all. So as I said, it is the great moment for all of us. And as Dr. Tripathi has mentioned, today is the birthday of C.V. Raman. So it can't be a better time than this to organize this real lecture. As you know, he was known for his work in the field of light scattering. Using a spectrograph that he developed, he and his student discovered that light traverses a transparent material. Reflected light changes its wavelength and frequency. This phenomenon they called modified scattering and was subsequently termed as the Raman effect or Raman scattering. He received, that what he mentioned, 1930 Nobel Prize at the age of 42 in physics for the discovery and was the first Asian to receive Nobel Prize in any branch of science. Tamil Brahmin parents, he did his school education from St. Aloysius Indian High School, bachelor's education from the University of Madras, and master's from Presidency College, Madras. His first research paper on diffraction of light was published way back in 1906, while he was still a graduate student. So our students should take inspiration from his work, and this is the high time that these stalwarts will ignite your minds. And I'm not surprised that we may get one of the Nobel laureates from this hall only. Joined the Indian Finance Service in Calcutta as Assistant Accountant General at the age of 90. There he became acquainted with the Indian Association for the Cultivation of Science, that is IACS, research institute in India, which allowed him to carry out independent research and where he made his major contributions in acoustics and optics. In 1917, he was appointed the professor of physics by Asutosh Mukherjee at the Raza Bazar Science College at the University of Calcutta. He founded the Indian Journal of Physics way back in 1926. He moved to Bangalore in 1933 to become the first Indian director of the Indian Institute of Science. He founded the Indian Academy of Sciences. Same year, he established the Raman Research Institute in 1948, where he worked to his last day, that is the 21st November 1970. It was the vision of the Director Professor Tripathi of the Institute of Science to celebrate the birthday of Sir C.V. Raman with Nobel Prize winning work of the current year so that all researchers of the institute gets familiar with the cutting edge science that was done by the Nobel laureates and the young minds are ignited to jump into the field of science. This year's Nobel Prize in Physics was awarded to Pere Agostini, the Ohio State University, USA, Pink Rose Max Planck Institute of Quantum Optics, Germany, and N. Müller from the Lund University, Sweden, for their experimental methods that generated attosecond pulses of light for the study of electron dynamics in matter. Through their experiments this year, laureates have created flashes of light that are short enough to take snapshots of electrons' extremely rapid movement. Nobel Prize in Chemistry this year was awarded to Mongi G. Vivendi, Massachusetts Institute of Technology, that is MIT, USA, Louis A. Brust, Columbia University, New York, and Alexei Yakimov, Nanocrystals Technology from New York, USA, for the discovery and synthesis of quantum dots. Early in 1980s, Alexei Yakimov succeeded in creating size-dependent quantum effects in colored glasses. The color came from nanoparticles of copper chloride, and Yakimov demonstrated that the particle size affects the color of the glass via quantum effects. A few years later, Brus was the first scientist in the world who proved size-dependent quantum effects, particles floating freely in a 1993 Mongi Vivendi revolutionized the chemical production of quantum dots, resulting in almost perfect particles. Quantum dots now illuminate computer monitors and television screens based on the QLED technology. Biochemists and doctors use quantum dots to map biological tissues. The 2023 Nobel Prize in Physiology or Medicine was awarded jointly to Katalin Kariko, University, Hungary, and Drew Weissman, University of Pennsylvania, Philadelphia, USA, for their discoveries concerning nucleoside-based modification that enabled the development of effective mRNA vaccine against COVID-19 during the pandemic that began in early 2020. They have fundamentally changed our understanding of how mRNA interacts with our immune system. This will be a true academic feast for everybody who are present here and who will be viewing through YouTube. I am certain that besides propagating the knowledge, this will bring excitement towards working in science. Our knowledge is poor, and we have to go a long way to understand the mystery of nature, and thus, such academic feasts will bring new minds to sciences in our country. I wish the function a success, and let us hope for a bright future for our nation. Thank you. Jai Hind.
Raman scattering is an important discovery that paved ways for several future scientific developments. Had it been seeing to sensing, had it been medicine to minerals, had it been from static to transport property, whether the goal is qualitative or quantitative, Raman analysis can provide key informations easily as well as quickly. We have a very small video which talks about Sir Raman's brief interview and interactions with students as well as a journalist. I would request you guys may come on.
and his more recent discovery of the origin of floral color. Nature, you see, does her best in the garden. She is putting out her loveliest for our benefit. Up to us, try and understand what she does, why she does it. To find, you see, the world around us is full of objects. I look and I got that bunch of different flowers. It's an amazing sight. Hundreds of flowers, all identical, all showing the same lovely blue color. Why did I look at this lovely blue color? I could wish I could send you the bunch of that. I got a piece in front of you. I said, why is that? Why is that? They say, that's how it started for you, and I was started with the friend. I've gone on with other things. So that's a good point. See, the real science begins when you are really interested in something and you want to find out. You know, the one with the but no, the one which always been shouting at me. So here I am. Now tell me why do I show these facts? Because ultimately it was this power was responsible for my putting forward these new ideas. You can't get away from the fact. This is a Stephanopoulos picta, it's called. Stephanopoulos picta. That's the name of it. I got it from a gardening book. I discovered the discovery of the floracos. The colors are due to this amazing substance. What is responsible for the floricolor is not one completely new. And they are the origin of floricolor. And the origin of floricolor. And the requisite evidence is that and then I will find out having got it, I got it. In what it is, what is the living substance? How does it keep that? And I thought now it must be a evidence from the behavior of this carbon. And there it is. And I will come forward with this. So I believe that and I look at all the literature, see the everything of literature to do aggregated support. And here it is. What is it? Same position, same substance. High pressure, you don't expect to cover food and more pressure. High pressure band, high pressure CO carbon monoxide band. This sequence of line from the precise number of the precise position and the precise intensity I want. Not underlying the need and they just thinking, you know, in fact, I have insulated myself in this garden. Simply getting me to think without me. And you will come and disturb me. You see, it needs a certain
Thank you for hearing it patiently. You might have seen how nicely he has talked about, picked up a flower and talked about the scattering through colors of the petal using a very small handy spectrometer. So over the course of this event, we have meticulously curated series of lectures that will provide profound insights in pivotal discoveries that have earned this year's Nobel laureates their esteemed recognition. The lectures will be led by the distinguished experts in their fields who will illuminate the significance and the impact of laureates' contribution, fostering a deeper understanding of cutting edge research. In order to begin the series of lectures, I now request the head, Department of Physics, Professor Sanjay Kumar sir, please introduce the eminence of our first speaker, Dr. Gopal Dixit, to the audience, sir.
Thank you, Archana. So, ladies and gentlemen, it is an absolute honor to introduce our distinguished guest speaker today, Dr. Gopal Dixit. Dr. Dixit is a renowned physicist and researcher with an impressive academic background. Earned his master and bachelor degree from the University of Allahabad. and completed PhD at the Indian Institute of Technology, Kharagpur. His career has taken him from Hamburg, Germany, where he worked at the Center for Free Electron Laser Science, to the Max Born Institute in Berlin, and eventually to his current role as an associate professor at IIT Bombay. Dr. Dixit's research is at the cutting edge of ultra-fast processes, with a focus on topics like petahertz electronics, quantum technologies, and graphene valuetronics. His work has been published in top journals such as Nature Communication, PNS, PRL, etc., and featured in prestigious media outlets including MIT Technology Review and NBC News. In addition to his research, Dr. Dixit is known for his exceptional teaching skills, having contributed to both undergraduate and postgraduate education. He is the head of Ultrafast Research Group at IIT Bombay and serves as a research ambassador of DAD, Germany, India. Dr. Gopal Dixit's accomplishment extended beyond academia. He is a sought after speaker, recognized for his critical thinking and ability to foster collaboration. His earlier roles in institutions like DAISY in Hamburg and MBI Berlin showcased his ability to turn innovative ideas into practical applications. With numerous prestigious fellowships, including Marie Curie, Raman and DARD Research Ambassador Awards, Dr. Dixit has left an indelible mark on the field of ultrafast process. He is one of the leading experts to provide a concise and comprehensive overview of the work of Nobel laureates Val Agostini, Franz Cajus, and Annie Hillier, who were awarded the Nobel Prize in Physics 2023 for their experimental contribution in generating attosecond pulse of light, instrumental in studying electron dynamics in matter. Please join me in welcoming Dr. Gopal Dixit, who will undoubtedly enlighten us with his groundbreaking insights in the realm of ultrafast process.
Thank you, Professor Sanjay Kumar, for your kind introduction. And at the same time, I would like to first thank Professor Tripathi for his kind invitation, Professor Sukla, my esteemed fellow colleagues who are going to give two other talks, respected teachers. Let me start. So, as we are celebrating the Raman centenary years, so I thought what could be the better title than attosecond physics? And what is attosecond physics? Is nothing but let there be a light and electron. So, whenever we see something around us, there are some processes which are too fast to resolve by our naked eyes and which are too slow that we can see how the changes are occurring in nature. Like we can easily see that when the day is changing from afternoon to evening to night, and then we transit to next day, seasons are changing. So these are the slow processes, but there are some fast processes. So let me first bring one of the very simple process which people have puzzled for the years, and this is what brings the first ultra fast, so-called ultra fast dose. Before that, let me again remind you that Nobel Prize for this year has been given to Annulier from Sweden, Franz Krauss from Max Planck Institute, Gark in Germany, and Pierre Agostini from Ohio State University. The work he did when he was in France for their experimental method to generate attosecond pulses, explore the electron dynamics. So, around end of the 19th century, there was a open question during the horse race that when the horse is running in a race, whether the four legs of the horse is in air or not at any instant. That is what is called galloping horse. And then this scientist, Mayopride, he designed a camera with faster shutter speed, and what he did, he started capturing number of images. So you can see this is the different instances during the race, and you can see that there are some instances when the four legs of the horse is in the air, and that's how this issue was resolved, and this research was published in a research paper by E. Mayobridge from Stanford in USA, and that is the title of the paper is known as a running horse or horse is in race something. Now in these days, let's fast forward. Fast forward. These days you have a much fast camera, and you can take different instant. For example, in this particular instant, you can take different instant and you put together, and what is called, you can make a spectroscopic image. So these are the things that we call as a macroscopic object, which you can see either by your naked eyes or by the camera that you have in your hand. These days you can buy from the. But what about if you go to the microscopic object? For example, electrons or atoms or molecules. So let's first me give the, this is what is known as an attosecond. So this is 1/billionth of the billionth of the second. So here you see that this is 10 to power minus 18 and here 10 to power 18. So now we have covered the two extreme spectrum of the time axis. Now if I zoom between 1 attosecond to 1 second and see what is happening in our surroundings. So this is the zoomed picture, and we can start seeing that around 1 second we have the stopwatch. Now if you go to much faster, or let's say another faster, that is the shutter speed of your camera. Now 10 to power minus 6, which is a microsecond at which your solvent and solute kind of reactions are happening. If you go to the nanosecond, this is the time at which the electrons or all the processings are working in your all the electronic gadgets or devices. Now if you go to even higher time scale, 10 to power minus 12, that is a picosecond. This is the time scale at which your atoms start vibrating, rotating, moving in your matter. 10 to power 15, which is a femtosecond time scale. This is the time at which light falls on the green leaf, water is split into H and OH, and this releases energy, and this is what we call as a photosynthetic system, energy release, or the new way of energy. And then the fastest time known to us, what people can see it in experiment, is the attosecond. This is the time at which electrons are moving in atoms. So to give a number, because just all the time telling attosecond, let me give a very simple idea. So this is the simplest system that we know, that is hydrogen atom. So this is a Bohr picture. Nucleus is here. Electron is revolving in so-called circular orbit. And if we calculate this with using 10 plus 2 level of simple mathematics, we know that the time it takes to complete one revolution is 150 attoseconds. And the length of this Bohr radii is around half an angstrom. Of course, this picture is not correct because electron never revolves in a circular orbit. Everything is quantum mechanical. So now if you want to see what is the time scale in quantum mechanics way, so you just write down simply the energy labels 1s, 2p, ds, 3p, and so on and so forth. And we know that this is what is known as the Bohr formula. Energy is nothing but 13.6 divided by n square. And if you calculate what is the energy spacing with these two labels, you can easily get it around 10.2 electron volt. And now you convert this energy into time using energy time uncertainty, you will get 400 attoseconds. So this is the time scale that we are talking about. But of course, you say that why should I care about hydrogen? Hydrogen has nothing to do in my life. Okay? So let's come to some complicated molecule. So this is some molecule for biological use. You don't need to bother about the name of this molecule, but you see that you create some kind of disturbance in a simple language, and this is the electrons probability or charge distribution sitting here at t equal to 0, and you see that in 5 femtosecond it has moved all the way to entire molecule. Okay? So this is what we call as a charge migration. So electrons is moving from one end of the molecule to another end of the molecule along all the bonds, along the all molecular effort. Okay? So this is the snapshot of this conformer glycine and SCS3. You don't need to bother about this technical. So here is the landscape of this what is called ultra fast and ultra short, and here this is the time axis and this is the length scale. So here is the atoms which are the picometer and the attosecond. The electrons are in the nanostructures, electrons in molecules, electrons in some kind of peptides, and these are moving on different times, and they have a different length scale. This is a very nice review paper written in 2009 by the Nobel laureate French Krauss and my mentor Misha Ivanov. This is one of the highly cited paper in this field of attosecond. So let's come back and see what the light has done. So of course, before the invention of laser, most of the light source were incoherent. So in 1960, Mann has created the first ruby laser, okay, with certain frequency omega, and immediately people thought, okay, for certain kind of experiment, I need some different frequency. For example, you have this red pointer, it has a certain frequency, let's say 700 nanometer. Now you have also seen more fancy laser pointer which are in green in color, right? So what you do, you just double the frequency. It means that you reduce the wavelength by half. Okay, so this is what is called frequency doubling. So you absorb the 2 photon of omega of red color and you emit a photon of 2 omega with the green color, and this is frequency. Some of you may have seen also what is called a blue pointer. Of course, blue pointer is difficult to create. It's very expensive. Because why? Because it needs to absorb 3 photon, and 3 photon has to be emitted as a 3 omega. And that's why the creating the blue LED or blue laser pointer is difficult. It's quite expensive. Okay? So immediately after 1960, Franken and co-workers have generated what is called the double frequency generation. And if you see the result published in this paper, Physical Review Letter in 1961, you see that this is the omega signal coming out from the omega light. And this is the signal coming out from the 2 omega photon. And actually, when the paper got published, the editor thought that this is some kind of dirt, so he removed this small. Because it was so tiny that it thought that it's some kind of error. It's like that when you read the textbook and some mosquito comes and you put it and the mosquito comes out, then you think that this is what has happened. Later on, they have pointed out by this arrow, no, there is some signal at this. It means that all the higher order processes are much, much, much weaker. And that was the beauty of the Raman scattering also, because Raman scattering was 10 to the power minus 7 times weaker than the fundamental or the Rayleigh scattering. Observing the weaker process is always a challenge. Okay? So that was the story in 60s, 70s and 80s. And this is the first surprise that Anloulier has measured in France, and that was the first surprise. You see, these are the higher order tones. So this is the third, this is the fifth, these are the 7th, 9th, 11th, so forth. And you only see the odd order harmonic. There are some technicalities because inversion symmetry does not allow you to observe the even orders. But one was the surprise that all the harmonic, all the signals have the same intensity. Whereas the conventional wisdom says that every higher order process has to be much, much weaker. You have seen the second order signal was much weaker. It was like a dirt in front of this big dot. And that has puzzled the people. So this result came out in 1988 and it started puzzling the people. Why it is happening. At the same time, there was another advancement was going on. So this was another advancement. People were trying to shrink down the duration of the light. People were making shorter and shorter flashes of the light. So you see that in 1960, this Mann created, the pulse was, laser was lasting only 100 microseconds. And over the years, you see that people have reached to a realm of the femtosecond. And this is the time when this is called chirp pulse amplification. And if you some of you know that Gerard Munro and Donna Strickland got the Nobel Prize just exactly 5 years back for CPA. Okay? So now these days, up to 2000, this is a conventional setup of a laser. And if you take the most of the common laser these days with wavelength 800 nanometer, and if you convert the 800 nanometer wavelength by 2 pi omega, you will see that the time come out to be 2.66 femtosecond. And that was the rigid wall. People always thought that we will not able to cross this. That is the ultimate limit that we have reached, because there is no way. And that you see this flattening. This flattening was going on for decades and decades. So there was two surprises. First, Unluli has seen that some of the higher order signals have the same intensity than the previous order. People don't know what is happening. There was no explanation. And then there was another thing, that this hard wall was difficult to break, and people thought it cannot break. So what people have thought? This is the typical spectra of higher order harmonics. This is the schematic. And you see that the first few things are dropping out. So this is what is known for the conventional wisdom, but the plateau was not explainable with the conventional wisdom, and there was a cutoff. And there was another surprise, that this cutoff has a universality. So this was the universal behavior. People don't know how this is coming, but this was the universal behavior that people. So the first successful explanation was given by Anlulia, Ken Safer from LSU, and Ken Kullender in 1991. Then the most simplistic explanation given by the Paul Korkum from Canada, supposed to also get a Nobel Prize, that this is your electric field. So light is nothing but electromagnetic radiation, means electric field is there. So this is the electric field oscillating in time. You see, you always write E cos omega t. Now this is your atom. So electrons are bound by the Coulomb potential 1 over r. When the electric field is zero, you see there is no perturbation. But once the electric field changes its sign, your potential becomes distorted. And then electron has a probability or the possibility to come out. Because here electron cannot come out, because everywhere is the potential. But at this point of time, electron can come out. And once it come out, it becomes free, and it is oscillating in presence of the light. And whenever any charged particle oscillates in presence of the light, it acquires some energy. Okay? And once the direction of the light field changes, again you bring back the potential back, and electrons come back and recollide back and emit the radiation. This is what people have described as a three-step model. So the first step is the tunnel ionization. The second is propagation. Electron is moving in presence of the light as a free, and the third step, it come back its home. So like a homecoming. Okay. So this is a schematic in a more detailed way. So you see that this is one cycle of your light. Once it reaches to the maximum, your potential has been perturbed significantly, and electron is coming out. Once it goes to the zero, your potential comes back to its original position. Again, it changes its direction, it recombines. So this is another successful explanation that came out in a very simple way, and people can visualize it, people can successfully understand. And this is what people call as a three-step model, primarily given by the Paul Kortum and numerically verified by the Ken Cullen in around 92. Once you have this high harmonics, let me give a very simple, because when we say that we are physicists, if you don't write any equation, it makes no sense. At least let me allow write one simple equation. So this is a force, this is acceleration, double derivative of your position, which is exactly like electric field times charge. Charge is 1. Okay. Now if I do the one integration, you guys will get a velocity, and once I will do another integration, you will guys get a position. And in integration, you will have a two limit, lower limit and upper limit. And because of using lower limit and upper limit, you can see that there are different instances of time at which the electrons are coming out from the system. And this zero means that electrons are returning back to the system. These are what we call as a trajectory. And once you know these trajectories, I can take the velocity, I can square it. And once I square it, you see that the maximum kinetic energy I will get 3 eV. That was the cutoff, universal cutoff. And that's why the Paul Kortum got famous, because of writing these three equations. That indeed you can explain in a very simplistic way that why the harmonic spectra or the overtone spectra behaving same for different atoms. So this was the high harmonics. People thought that yes, we can high harmonics. And the successful quantum description of this process was given by my previous mentor, postdoctoral mentor at MBI Berlin and long-term collaborator, who also supposed to get a Nobel Prize. Then this is the process. Atoms are coming out from a gas jar. You shine a laser. Every atom is emitting different kind of radiation. And once you have in constructive interference, you will have different kind of. This is a typical high harmonic spectra I showed you. Now, if you select a few harmonics, so this is in frequency domain, and you change into time domain, you will get pulses. So these are the pulses. Now the question comes, what is the duration of the pulses? It's like that you create some kind of material, but you need to characterize the material, right? You cannot say that I have created unless you will verify it. So there has to be some kind of measurement techniques which has to be ensured that these are really attosecond pulses. It can be anything. Okay? So how to measure the attosecond pulses? So let me come very simple starting point. We all know that Albert Einstein has successfully explained photoelectric effect. What is the photoelectric effect? Here is the atom in the system. This is the ionization potential or the work function of your system. And if you shine a light which is larger than the ionization potential, electron will be removed. Okay? So electron will be removed. Now the same process, so only one light has coming or one photon. The same process can be done with the 2 photon or 3 photon if energy is not sufficient. So these are called photon or multi-photon. Of course, every higher order process is much, much weaker. Remember, I told you, these are the multi-photon. But then, in around at least, Pierre Agostini observed another interesting observation, which he has used later on to characterize the attosecond pulses. What he has seen, here is your atom, this is the ionization potential. It has absorbed 5-6 photons, and the electron is supposed to be left out the system, but this is not happening. Electron is still absorbing more and more and more and more photons, and this is what is called above threshold ionization. Why? Because electron still feels the photon potential of the atom, and that's why it still keep absorbing these multi-photon even after coming out from the threshold. So that was the idea that he has utilized. So this is the attosecond metrology that people call, pioneered by Pierre Agostini and Anlulier in 2001. So what they have done, that you can remove the electron either by absorbing a big photon omega, or you can reach this path by 2 smaller frequency, another photon, or bigger frequency, and one and you emit it. Instead of absorbing it, you emit it, and you can reach this path by all the 3 processes. The 1, 3. Okay, and this is what called as a rabbit. So what is the rabbit? I will come back to you. So you see that these are the harmonics which you are absorbing by the blue lines, but the additional part you are coming in between by absorbing 1 photon and emitting 1 photon emission, and this is the one interference of these 2 we call as a sideband. These are the sidebands, okay? And these are the sidebands that you observe. So by doing this schematics, this is the first paper by Pierre Agostini in 2001, where he has measured these different harmonic, 13th harmonic, 15th, 17th, 19th, and these are the small sidebands, something in between the 2 harmonics. Remember, something in between the 2 harmonics, 2n plus 1, 2n minus 1. This is the sideband, this is the sideband, these are the sideband. And what he has measured, that indeed you have the train of attosecond pulses which are 200. So that is the first clear evidence that indeed you have attosecond pulses, and they have broken the hard wall of 2.67 femtosecond in 2001. That was the Pierre Agostini, and the technique has a funny name. It's called rabbit. It has some full abbreviation. At the same time, by the way, this is in frequency domain. But these are in frequency domain. At the same time, French Crouch come up with another idea, because whatever you can do in frequency, you can also do in time, because there is time frequency uncertainty. So whatever you can do it one aspect, you can do another aspect. So French Crouch has done something is called streaking. What is the streaking? Means that you strike out, like in carom, you strike something. So you remove the electron, and this electron will be streaked out with this pulse, with this light, which is shown as this big one. And this is the electric field of your attosecond pulse. And what he has measured, indeed he has measured the single attosecond pulse of duration 530 attoseconds. And at the same time, he has published this paper in Nature in 01. 2001. Okay. So both the groups simultaneously got the attosecond pulses. But now the question is that, so what? I create something, but whether it has some useful or not. The Nobel Prize is not given to create something. I mean, I can create some new building, I can create something, but whether it has some useful, whether it will change your conventional mindset. So one of the question that they have done it, which has changed the basic concept, is photoelectric effect. Photoelectric effect started from 1905. Einstein got a Nobel Prize in 1921, and photoelectric effect, if you go and read any textbook starting from 6th standard or 9th standard, what it is says, you shine a light with enough energy, electron will come out immediately, instantaneous. It's immediate process. Means that electron start behaving or experience the light immediately. There is no time difference for that one. Because those days, everything which they cannot resolve is instantaneous. Whatever you cannot see is instantaneous. Like if you switch on the fan with high speed, you cannot count how many wings it has. It's like a continuous circle is rolling. And that was the concept. And that's what these people had broken. So, as I said that this is a photoelectric effect. Electron will come out, and this is what is called instantaneous. So what they have done, of course, hydrogen is not possible because making a nascent hydrogen is difficult. You can have hydrogen molecule. So what they have done, they took a neon molecule. It's always easy to do experiment with the neutral gases. And what is the neon? Neon has a 2 electron in 1s, 2 electron in 2s, and 6 electron in 2p. And they have shined photon energy attosecond pulse with 106 eV, which is enough to remove either from the 2p or 2s, but not from the. So either electron can come out from 2s state or electron can come out from 2p state. And now from your conventional wisdom, what you will see, which electron will reach to the detector first? Of course, from the 2p, because 2p will have a more kinetic energy. 2s will have a less kinetic energy. That is your conventional wisdom says. If you think about which is reaching to the detector faster. But using the same streaking technique, Franz Krauss in 2010 showed that no, this is not the case. 2s electron is reaching to the detector faster than the 2p by 20 attosecond. Of course, there is an error bar, but 20 attosecond. Immediately after this one, there was a huge debate in the theory and experiment because there was no theory which can successfully explain this measurement, even not half of the number. And that was the time when I started this field. Unluly, series of experiment in argon. As I said that it's easy to do experiment in inert gases. And you see that these are the different energies of your light attosecond pulses. These are the experiment, and these are the different kind of theory. And none of the theory and experiments are matching. And that was the time when there was a serious doubt that whether the meaning of the time is meaningful or it's useless. We are debating something useless things. And this is the time that first we published this paper in Physical Review later in 2013, which has been cited by Nobel laureate. And this paper we have published not by our mentor but with our collaborator. And then another successful paper in 2015 where we have showed that no, the measurement done by Unlulier is correct and we can successfully explain their data. And that gave the confidence to them. Moving forward after 2015, in 2016, Unlulier repeated the experiment in argon, and that time I was in GRC USA when this data was discussed. So Franz Krauss did the experiment in 10, Unlulier did in 16, 17, and you can see that all the data are now explained with the, that partially we propose and partially some other people contributed. And once it has been established that indeed in 2017 attosecond pulses has been generated, attosecond pulses has some meaningful use that it can do a time delay. So what is the time delay? So it's like that you are standing here and light means electromagnetic field means electric field. Electric field always exert a force on you, right? So it's like that you are standing, I will push you. When I will push you, you will try to feel the force exerted by me on you. And then only that, then you will react whether I should fall down or I should will stand it. Now, atoms have many electrons, so means that you are surrounded by many people. Then there will be a situation that some people will try to push you and fall down. You can sometimes some people support you, and whatever force I'm exerting on you, still you will keep standing. So this is what we call as a response time in light matter interaction. So how much time an electron is taking to respond when light is shined on the sun. And this study is not limited to atoms. There are a number of applications. I don't want to go it, but this is related to something. In mathematically, this is a dipole amplitude. You are measuring the phase of the amplitude, and because time is not a measurable quantity in quantum mechanics, you are measuring the phase. And what is the phase? Phase is the one that is accumulated in presence of some kind of potential. This is just for the expert people. We can discuss more detail later. So, as I said that after this neon, this has opened a new way to investigate electron interaction in matter in time. Okay? Now, people have also, so this is another work that we have done, that we can take the atom and put it in fullerene and see how the case is affecting. So this is a physical review letter 2013 by us, and how fast the electron can reach to the detector. People have also looked this experiment from the French Krauss group in tungsten. So they have looked whether the electron is coming out from the localized 4FH state or delocalized conduction band state, and you see that the time they are measuring is 110 attosecond. So this is what we call as attosecond 1.0. So you can address lot of basic questions imposed by the quantum mechanics or your conventional wisdom. Now we are into the attosecond 2.0 era, which we are going to bring revolution in technology. So what are the things? So let me bring, so in 2011, people have started measuring the high harmonics in solids also. So this is a paper by David Rees from USA. We are collaborating with this group. Pierre Agostini, you can see that he is also here. Sambhu Gimere is the first one. So let me come back and quickly give a glimpse that what our group is doing over the years, in last 8 years, and pushing this boundary of attosecond in India. So we know that electron has a charge. This charge can be used to make different kind of transistor, and that's what we call electronics. Electron can also have a spin, and we can manipulate the spins, and we have a spintronics, and there are a number of devices that spintronics does. Now in 2D materials, so this is a 2D material, some kind of MOS2, and if you look its band structure, it has a finite band gap, and if you look at the Brillon-Jones boundaries, there are some minimas or maxima. So here is the maxima, and here is the minima, and this is what people call as a valley, because these are the valleys in the 3D material. And what people thought that we can do some kind of excitation. So what is the idea that people have come up? That okay, so this is my values at k and k prime. I can do some kind of excitation at k without affecting to the k prime, or I can do the same at k prime but not to the k. And this I can see as a 0 and 1. So what? It's like spin up and spin down. So what is the new thing here you are doing? But what we can do more, we can create a linear superposition of 0 and 1. And once we are able to do it, we are into the quantum technology. The superposition is the first step in our case, because you see that at phase 0, this light fits with one valley, but it doesn't fit to another valley. But at 90 degree, it fits with the k prime valley, but not to the k valley. And this is what we have used it to create the valley polarization. So this is the valley polarization result, that we can modulate the valley polarization from one value to another value in pristine graphene with 0 band gap. And people have done the experiment in Barcelona. Okay, and once this result came out, we have also created what is called valley transistor. Immediately our paper started coming out in USA, and then our paper becomes one of the top trending things in quantum technology in 2020, because you can really create something graphene which people have created, that this is a dead material because it has a 0 band gap. This is a incorrect assessment of the graphene, because graphene has the highest carrier mobility. So we have created also a Valley transistor using a series of laser pulses. Why these are useful? Why we are excited? Why this will bring a new change in technology? So we all know quantum computer is something very useful. Our government has put a lot of money. So these are the two working quantum computer, one based on the trap ions, one based on the superconducting qubits. These are the transmons, these are the trap ions. Why people have kept this quantum computer in ultra cold temperature? What is the reason? Because you have prepared something and you want to do some kind of measurement before it destroys. Why it will destroy? Because other molecule will comes and destroy it. There are a lot of scattering collisions in that. So whenever you reduce the temperature, you reduce the probability of collision. Like gas, if you reduce down the temperature of the gas, the motion of the gas molecules changes. That is the working principle of Einstein. Okay? But what if we can do all the measurements on a much faster time scale before anything destroyed, and that too in room temperature? And that's what the use of attosecond or ultrafast technology. That you can do everything in 5 femtosecond, 10 femtosecond, 500 attosecond, number of time measurement, number of time reading and writing before anything destroyed in graphene, in 2D materials, not creating this bulky setup, so that in future you can have a quantum computer like this laptop. So this is the first promise of the attosecond technology. The second promise of the attosecond technology, we have also looked how the defects are playing a role, how the Majorana fermions can be seen using attosecond technology. What about the while? There are fundamental questions and so on. So let me how the attosecond polarization. So these are the few glimpses of our work. We can not only measure something, but we can also the imaging. So this is going from 3D to 4D. So this is the first paper in PNL that we wrote, that you can create a movie of the electronic things, how the electrons are moving. Then later on we wrote another paper in Nature Communication, that how you can see how the bonds are broken or formed. So this is a very basic question in chemistry, whether the breaking of the bond and formation of the bond happen at the same time or not. Don't know, but now we can see it. And once we are able to see it, we can control the chemical reaction. Because we can control which path we want to guide our chemical reaction. So this is a coherent control of the chemical. Okay, so let me tell you the future, another future. So what is the processing speed of your laptop from last 15 years? There are a lot of senior people. Any number, please tell me. Gigahertz, right? 2 gigahertz, 3 gigahertz, 4 gigahertz. This number has changed from last 20 years? No. Only first digit has changed, but the gigahertz has not changed. But because the technology has saturated, the CMOS technology has saturated, there is no way to cross this limit. It's like this femtosecond boundary. You cannot cross this. What we are doing, that instead of using this CMOS technology, drive the electron, generate the current in semiconductor technology using light. Let's say 800 nanometer is the wavelength of your visual light. Convert into frequency. What is the frequency? You will get it. You will get it 10 to power 15 hertz. What is the 10 to power 15 hertz? This is petahertz. Petahertz. Change from gigahertz to petahertz. It's a 6 order of magnitude enhancement. So if you can devise, that's what community is doing, including the French Krauss group, that we can devise the new kind of semiconductor devices, not working on the RF technology, but based on the light, then we can improve the processing speed, not by the 1 order of magnitude, but at least 3 to 4 order of magnitude. And that's what we call as a petahertz electronics, or what we call as a light wave electronics. Light wave electronics or petahertz electronics is another new dimension that attosecond technology is developing, and we all are contributing along this direction. So indeed, attosecond physics has a bright future. Thank you very much for your kind attention. So I'm grateful to all my group members, attosecond physics group at IIT Bombay, and collaborators at IUNO, has been pioneer to drive this attosecond physics. In this audience, if you guys are interested to do something in attosecond physics, feel free to write me. We always have some position for PhD and post. Thank you very much.
Thank you so much, sir. It was indeed wonderful presentation. We can take a couple of questions from the audience, please. If no question, I have a question. I couldn't resist asking question because it's interesting. You have talked about using these attosecond pulses for quantum, especially for coherence, I believe.
Yes.
Because you're talking about superposition of the states and how
we can also create entanglement. So people have done the Belly state in atoms. We are still figuring out how to create a Belly state in solid state sample.
these valley transitions, how stable are they? I mean, if we want to use them as qubits,
they are stable for 50 femtosecond.
defense.
After that, it will recover. So 50 femtosecond at least, if we do a repetition rate of 1 femtosecond each measurement, we can do 50 times.
Yes.
And what I learned that, for example, while semi method, the scattering time is much longer, like picosecond. So there you can have hundreds of times much faster. So these are the first steps. So like in 1960, people have created the laser, and nobody knows that down the line of 60 years we will have a laser pointer. So this is what we are driving.
We have one question, Anshul sir.
So this is important to clarify that I'm doing theory, and attosecond physics in India is in fingertip. So there are only, I am a theory people, and there are two more who are just setting up their lab. There is nobody in India who is attosecond. So this is a pretty new topic, and it's a very difficult topic to grasp. So there is one group in Aishar Mohali led by Professor Kamal Singh, and then there is another group in PRL Ahmedabad led by Rajesh Kushwaha. Rajesh is from Banaras PHU.
Any application in biological field? You see any applicability of this technology in biological field?
So I will not go into deep biology, but whatever my limited understanding is this. For example, let's say we have rhodopsin in our retina, right? And we are able to see the object around us when the light falls on our retina, and rhodopsin goes from cis to trans isomerization. It goes from 11 cis to 13 trans. Okay. How this goes, people don't know. It has happened. Now, what we are doing, we are trying to understand its internal mechanism. And once we are able to understand the internal mechanism and make sure that we can drive all the cis to trans 100% efficiency, then we can create artificial so-called retina. That is one thing. The other thing which is very useful, that water is splitted in photosynthesis system, and there is something is called Koch cycle. Its manganese is used as a catalyst, and it goes 4 steps. People don't know what are the 4 steps. Once we are able to understand the 4 steps, we'll create artificial Koch cycle everywhere. So these are the 2 examples, but there are numerous examples. If you are more interested, go to the web page of the French Krauss, one of the Nobel laureates of this year, and he has a one dedicated unit where he is putting the efforts to the biology, how he is tagging the molecule, the motion of the molecule.
We will just take one last question.
The way life has changed once you got a mobile phone, can track you everywhere. And once let's say the quantum computer will come in a more affordable way, one of the very important things which we don't care, but we always get affected by weather prediction. And we all know that nobody can predict weather accurately, whether it's USA or us, or the turbulence. So once we are able to have a much better, we are discovering new drugs, because you cannot do all the experiment in the lab. Lot of things done in the computer, then this has been taken to the lab. Once we have a much better quantum computer or much better processing power, then we can improve. And there the light or the attosecond or ultra fast light will come.
Thank you so much, sir. Let's thank the speaker one more time. Thank you so much, sir. I know you all have too much of queries like in time, so you can discuss that over the high tea. Speaker will be with us. Before we conclude, I would now like to request our director sir, our rector sir, and our dean sir to please felicitate our speaker, Dr. Dikshit. Thank you for bearing with us with patience. I would now like to request Dean, Faculty of Science, and Professor in Biotechnology, Professor S.M. Singh, kindly introduce the eminence of our next speaker, Dr. Sanjay Singh, CEO, Geneva Biopharmaceutical Limited, to the House.
Thank you, Ansh. Actually, this introduction had to be given by the coordinator School of Biotechnology, Mr. Pratyush Shukla. But today he had to go out, and this responsibility suddenly was put on my shoulders. And when I was called in the chamber of the director, Professor Anil Kumar Tripathi ji, Professor Chelapati Rao was sitting with me. I said, introduce a great man of our motherland, Bharat Mata, Sanjay Singh. I find myself as a real dwarf because he is a great achiever, a great scientist who has brought name and fame for us. But still, I will try to compile few of his, I'll again say few of his academic accomplishments because the list is so long that we're not able to decide what to include and what to exclude. Such a highly celebrated scientist, and today we are going to celebrate with him the Nobel Prize given to Carrico and Weizmann for their discovery, for their contribution to the understanding of mRNA-based vaccine. Professor Sanjay Singh himself is a contributor to the development of Indian mRNA-based vaccine. Before this, viral vaccines have fetched Nobel Prizes. 1951, it went to Thielen, and 1954, it went to Weller and Robbins, their discovery of virus-based vaccines. Dr. Sanjay Singh is the Chief Executive Officer and whole-time founder director of Genova Biopharmaceuticals Limited, which is a subsidiary of Emcure Pharmaceuticals. He has been associated with Genova since 2006. At Genova, his scientific expertise has led to the several innovations to life-threatening diseases, and Dr. Singh has been at the forefront for developing India's first mRNA vaccine for COVID-19. A loud applause for that. Genova's mRNA vaccine, Gemcovac TM19, as it is, has been approved by the CDSCO for emergency use. It is India's first mRNA vaccine. Not only that, world's first thermostable mRNA vaccine. Prior to joining Genova, Dr. Singh has worked at NIH USA, where he headed the antigen research section. He has won numerous laurels, recognitions. US Department of Health, Human and Health Services awarded him with Special Act or Special Service Award in 2005 and Staff Recognition Award NIAID NIH in 2000. Contributing towards national interests, Dr. Singh has served as member of the Committee of the Development of the India's Guidelines on Similar Biologics, constituted by the Department of Biotechnology, Government of India, and Central Drug Standard Control Organization and Ministry of Health and Family Welfare. Dr. Singh has completed his post-graduation in biochemistry from Lucknow University and PhD from CDRI Lucknow. So he's our man that way, really, the man of Indian soil. He has won many national awards. Recently, 2019, Honorable Minister for Commerce and Industry, Shri Piyush Goyal, and VK Paul member Niti Ayog gave him the Biotech Product Process Development and Commercialization Award in 1990. He has got many publications, many patents to his credit, for which he has been several times awarded Margi Patel Choksi Memorial Patent Award. I think I'll not read out the entire list because it's mammoth recognition that he has been receiving all the time. Few of them a little more. 1996, he received the much coveted Research Fellowship Award from WHO TDR, World Health Organization, Tropical Disease. Dr. Singh holds critical process technology and product patents in various geographies and have the potential to generate valuable forex, the unique ones that have been listed below. I'm not reading them, but I'll not come in between you and Dr. Singh because all of you are eagerly waiting to lecture. Once again, thank you, sir, for accepting the invitation and coming down to you.
This will do more. Yeah. How to reduce that? Thank you, Professor Singh, for your kind words. Thank you, Professor Singh, for your kind words. It's an honor and pleasure to visit BHU. And I was not in position to say no to Professor Tripachi's invitation. And I accepted it, but because of some government meeting came in between, so I have to jump on that from 3 p.m. onward, which also I cannot afford to go. Yes, science is a very, very important tool, and somehow there are many areas like finance, politics, management, everything was there, but in 2021, 22, 23 showed us science is the only way by which human can survive. And this is, we were able to curtail the COVID. And if the vaccines were not there, even the population would have been faced much more difficulty. Here for this particular lecture, I have one slide dedicated to C.V. Raman. And I want each faculty and each student should read it and understand it carefully. In science, only thinking is important because the essence of science is independent thinking, hard work, and not equipment. Please note it, not equipment. When I got my Nobel Prize, I had spent hardly 200 rupees on my equipment. And today this 200 rupees you can convert into 20 lakhs. This is, I used to, though we have a state-of-art labs, but still I try to explain to my youngsters who are in the field of innovation manufacturing that your critical thinking is very, very important. So on today, this auspicious day of his celebrations, I wanted to use this quote for you. So here, before going into the Nobel Prize winning work, a very simple, our body stores all the information in form of DNA. And DNA gets transferred from generation to generation and keep on improving. But storage information is like a software, and if you have to use something, you have to give a message, and that message is in the form of mRNA. And so mRNA is important. But mRNA, when it gives message, finally the body system works based on proteins do the job. For any act, protein has to be their job. So here,
somehow, if you make in such a fashion that you starting without your DNA, you start in giving the job work to the body. You don't need to have all these bioreactors, purification, protein, all that things that can go. So this is the genesis of the science, why it has been taken. So this prize has been given to them, and basically the prize was for nucleoside-based modification that enable the development of effective mRNA vaccine. I'll come a little bit detailed into it, but fortunately, I'm friend to both of them. And when I think he got the announcement, something like 3 a.m. in the morning, he called 5 people, and I was one of them. And the reason behind it that he said, I wanted to thank those people who have brought the product to market. Because of that, this recognition has gone so big. So what is the modified form? I just have given here. Unmodified is a standard base, and if you do some modification, then it stops inflammation. But still, this topic is a little bit controversial. But we want to celebrate here the Nobel Prize, and we have made some headway into that direction. So we do not sure that whether what we have done. So, but what is most important to see it here? The best-selling medicine was Humira, $21.6 billion, and one of the vaccine which was made by BioNTech Pfizer, which was she was the lady behind it. It sold $37.8 billion. So you can see like 300,000 crores. So you can see the level of business that are generated. So as my physicist colleague was giving a talk, it is science is the basis of all these things, but also science is the basis for making money and making the life easier, making just like if you can say iPhone or these things. But it has to be very competitive. Then only the possibility you can convert into a product, because what the people demand, how it impacts the society, those are the things are also very important. So when we are doing the science, it is also important we should continuously look into it. What would be impact, as Gopalji said, that impact is also demonstrated is very, very important. I come from the family of physicists, and I have shared with him. I am proposed of Raju Bhaiya, who is one of the main person from Allahabad University. And then my father was professor of physics. And then my son is at Oak Ridge National Lab, and he works on the quantum computing in physics. I'm the only one who has moved away and gone into the biology side. And my father was very tough on this. He said, you will not able to understand logic. I said, that much I have in genetic structure, so I hope I will be able to understand logic. So every area of science is very, very important because most of the people who get the Nobel Prize, they are not there. They have worked interdisciplinary in very different areas. They work in this interdisciplinary, and that's the outcome comes. So now moving into it, the history. The history is in 1961. Basically, the mRNA was discovered that this is mRNA from DNA to mRNA. Then how to deliver the mRNA, this was the quest. And they produced liposome. And then also they demonstrated from mRNA that you can make the translate in vitro. In the tube, you can make the protein. Need both machinery or whole system into this. And then to deliver this, the quest started this liposome, but it was keep on going in different ways. So if you give the mRNA, it gets destroyed. So the cap has been discovered, and then in vitro translation. So by 1980s, field was established basically that mRNA can produce the protein without the whole cell. In vitro, you can produce it. So the field started. And here I want to say you that this is very, very important factor because how you deliver it into body, that is important. So liposome was equally important. And then a lot of science started how to analyze commercially available T7 polymerase, how to make these enzymes in the industrial case, and all these things kept on going, kept on going. But here I wanted to say that in 1997, the first mRNA focused company was founded, and then some response came into the tumor cells, and then this is another company, CureVac, was founded, and I was watching it very carefully from here onward because it removes a lot of the in-between processes. You don't have to produce recombinant protein. You can just one step before and you can get it. This is one part. The second part, that when mRNA goes into body, then it uses its own machinery. So you produce exactly native protein what is required. So and the recombinant industry is at present around $400 billion industry. So you can see what kind of revolution it is going to bring. And in similar format, again, liposome came that you can make 4-component clinical trial started into this. Because this area was going into based on immunotherapy, especially for in cancer. Can you take a prostate surface antigen and make an mRNA and give it back and it become a vaccine? Something like this area was started for personalized cancer vaccine. At focus was, but some vaccination, some everything was basically in a struggling phase. Till in 2020, somehow the COVID hit, and then two groups started. One was when I was in NIH, next door was the Barney Graham lab who was working on that, and another group was this BioNTech where Katalin Kariko was working, and these two groups moved ahead. So NIH technology gone to Moderna, and the technology from BioNTech gone to Pfizer, and basically they converted into vaccine. And at the same time, because I was part of the pandemic preparation group of U.S. federal government, still I am, and when we saw there that in New York suddenly in one night more than 250 people died undiagnosed, the government of U.S. declared a pandemic. WHO was not able to understand at that point too. So from there, this effort into vaccine goes, and I called at that time our secretary, Dr. Renu Sarup, and I said that I would want to jump into this. I have the money, but I don't have that kind of money. So the world is changing, and thanks to our Honorable Prime Minister, and thanks to your Member of Parliament, even Banaras is changing, I have seen. And I sent a 5-page proposal, and I was given 25 crores grant. And the second one, because I think they believed into it, and the second when proof of principle we demonstrated, again 5-page proposal, and 100 crore single check grant was given. So thanks to Department of Biotechnology believing in me, believing in our science, and building on infrastructure. And so science portfolio is changing in the country, and I hope it is for good. Now, what is mRNA basically, if you want to say? So basically, you can put a gene of interest here. You can put 3' UTR, 5' UTR, and one is the tail, and basic cap. Cap stops not get degraded, and polytail is more for stability. But basically, this is a full small setup. And these are the vaccines which has been made by Moderna and Pfizer, and for which the Nobel Prize also won. We decided to use unconventional platform, so where we put them here ahead of this, and which keep on making this antigen couple of times, because we believe this is a different level of science, and hopefully paper is for minor revision. You will see the Nature Medicine is coming for our work, and I think Nature Medicine is one of the publications which has impact factor of 90 as compared to Nature. So I didn't send this paper to Nature. I sent to Nature Medicine. Nature has 42. And for this technology, I think 18th August of Nature issue this year has featured our technology for Genoa, that these are the 5 technologies which go. So we took an unconventional route, and we decided we will use this because what happens if antigen presence is for longer time? I think somebody said immunologist, antigen presence is for longer time, then you give better better memory to B cells and they mature for a better response. So basically, why DBT decided into it? This is vaccine platform, different vaccine platform, and this is vaccine 1.0. This is around 100-year-old. So Professor Jenner started it that you can take polio or hepatitis, heat and cold it, and give it to this. And this is also one of the vaccines which came in India, which is the vaccine from Covaxin. This has been made on this platform. But with development, scientific development, this has positive things, but it also brings some negative problem into it. The second generation vaccine, recombinant protein came and where seasonal influenza, hepatitis B, HPV vaccine, and this is where we came to know in 1960s that this is the DNA structure and this is by which you can make recombinant protein. And this is last 30, 40 years, this science is there. Third came, this is basically adenovirus based, which is primarily you can say DNA based vaccine. And here, one was emergency use authorization was there, but this is the second vaccine which was made by Oxford, AstraZeneca, and which was get manufactured in India by Serum Institute, one of the vaccines which made maximum impact. But we are here, we are in vaccine 4, and because of that, I'm a scientist first and business person, so I love to talk to my people and young students to see that you have to think forward, you have to think 10 years, 50 years, 100 years forward. Past is past. Past you can just little bit learn from it, not too much learn, otherwise you will be biased by their complexities unnecessary. So this is the COVID vaccine, and here three set of vaccine came. The first came from Pfizer, just because they were having big manufacturing might, and their funding was U.S. government funding was $10 billion on this vaccine. And then the second vaccine came from Moderna. Both are made in U.S. And the third vaccine is our vaccine which got approved. So first outside US and third vaccine global. So I will take you through a little bit of journey what this means. What is so important that here, yes, process economics is costly, but time to manufacture is nothing. You can start in the morning, by the evening the vaccine is made. This is the biggest change which has come in by this technology, and why this technology has been given Nobel Prize so quickly. Just 2 years before the technology has been implemented and ordered the Nobel Prize. And Drew was saying that I never thought in my dream that this can come so quickly, but the impact, because it has saved billions of people. So as I said to you that this is the open reading frame. So this is where modified nucleoside is there, few modified nucleoside. This is Moderna and I. Another company which I said was founded, CureVac, they were not using the modified and their vaccine did not reach the market. So they say that before, but we decided to use this self-amplifying mRNA and we have not used modified basis. And our vaccine is equally or better. So you'll come to see it. So because we added this particular part, so this is the Jimco-Vac, Vac 90. This was. So another part which I said, please follow it, that liposome. Liposome is very important. So this is a like lipid ball, and inside that they have entrapped the mRNA. You mix this high speed and it gets entrapped, but it makes a lot of losses also, and also it makes process little bit cumbersome. We went and we designed another part, and this is where we are very proud. We wrapped on the surface of liposome. And why we make wrap the surface of this is very easy, and here recovery is 99.5% of mRNA. In previous case, your recovery is only 70%. So when you make such a huge quantity, the price difference comes. And for this, we do. So ease of manufacturability. So this is the way we move ahead, and it's a very quick to make and very easy. And I will say what is the importance of this. Otherwise, if you have make to entrap, you have to make it both together. And here you can make the both component mRNA, keep it separate, make nanolipid separate, and anytime you want to mix it. And here my, I think, physics genes work, because how to wrap it on the surface uniformly, that was a big challenge for us. So now there was one problem with these two vaccines. They need minus 70 degrees centigrade. So when the peak period was there, Honorable Prime Minister was one-to-one, and he said that how we'll develop this cold chain system. And I said, sir, very, very difficult to develop nationwide minus 70, and you people can understand minus 70 is almost impossible to maintain and develop. So he said, what? I said, we will figure it out. It will not need it. I said, how much time it will take? I said, let's see how much time it will take. And constantly I was getting inquired by the DBD secretary that Prime Minister want to know that whether that succeeded or not. So I want to enjoy with young students what is the simple success behind it. So basically, everybody has these three kind of formats were there. Basically, this is the format on which the Moderna and Pfizer vaccine gone. So inside a nanolipid, there is small pockets where the mRNA has been kept. And if you see in an electron microscope, and this is somebody else was publishing at that time, what is the problem there? Not our publication. And you can see these are channels in which water channels in which the mRNA is there. And if you go by simple chemistry, so DNA is storage. You always have DNA for thousands of years. You can put DNA here, took out from after 1,000 years, and you can do the sequencing. And what is difference? What is difference between DNA and mRNA? It is this OH group. Only one OH group. And we used to say this is one stupid atom. And we went into deep chemistry of it, why this mRNA is degraded, and we figured it out that why this mRNA is degraded. And I'm telling you, this is the figuring out. This is hydroxyl group, phosphodiester bond. In presence of water, it goes and hit it, and its bases are broken. It was not published, not known. Simple critical thinking. Simple critical thinking. DNA, capping enzyme, all these things we worked around during this period, and we'll see there why we have done it. So this is the very, very important. So WHO started a term mRNA hub. If youngsters want to search it, they made mRNA hub. They invited us that whether you. So I said at present we are not sure of our technology. Once we are sure of technology, we'll part it. They said we are talking Moderna and Pfizer. I said nobody will touch you with wooden stick to WHO. Once these are multi-billion-dollar businesses, they are not going to share you with anything, and that is why this Atmanirbhar Bharat term is very important. We have to innovate for our own needs, and that can be only done through our institutes, our universities. I have a little bit difference because somehow in the last 4 or 5 decades in the country, a lot of money has been given to institutions, not to the universities. Because the brightest mind, young mind, which can be make mutable, is available in the universities. Institutes should be there for a mission mode purpose. But somehow I was part of some scientific deliberation Niti Aayog. I was also part of the deliberation of planning commission and a science and technology. I was looking into it. Most of the institutes in DBT, or most of the institute of ICMR, most of the institute of CSIR, most of the institute of DST, there are few buzzwords that they are going around. No, if we have made an institute for tuberculosis, they should only do tuberculosis in mission mode because they are funded too high as compared to our university. And hopefully you will see this era is changing now. If you are an institution, not universities, you should be focused to what to deliver. And yes, it is very, very important to solve our own problems. That somehow is missing, but with God's grace now it is, people must be feeling in the last few years this is changing. Technology can be placed because at the peak time, every country want to protect themselves, they don't want to share it. And here, I think our Prime Minister is very happy that we have done it, and he used our name in his UN address when he was in the UN. And these are the two vaccines. First was the primary vaccine, was Gemcovac 19. And then second is on Omicron, we used our endomythology a little bit more. We put it home, the Gemcovac home. This is the only booster vaccine available in India. This is booster. A specific vaccine has been made because the technology was not there, and because of that, we did it quickly so we can make any version any day. This is also have been approved, and thanks to most important contribution is the volunteers, and this utilized around 7,000 volunteers when the vaccine has been tested, and including us, because whenever product we make, we try to test on us whether it is right or not. And this vaccine was launched by the Honorable Health Minister on 24th of June. And here, if you see, these are the vaccines which are available in the country: Covishield, Covaxin, Sputnik, Zygo, Corbevax. This is Gemcovax Om and Gemcovax. Both vaccines are available on the global on the national portal. So this is what I wanted to say because of the space of time, that yes, it is very, very important to do the science best in the class, but bring it also to the use for the public. These are the two global patents we have filed. One is on the how to wrap the mRNA on the surface, and another is how to lyophilize it. So where we are going with this technology? So we have established this. We have established this platform. We have established this mRNA platform where still a lot of science we are going there. But we are also partnering globally for this cell biology, B cell biology, T cell biology, what is and protection. But what is most important, we made the first generation vaccine, we made the second generation vaccine, and we are also going to make a third generation vaccine. Further, we are trying to make vaccine better. This is one singlist dengue vaccine and malaria vaccine. We are working on make a better vaccine. But the most challenge is today is we are also started the program on tuberculosis. So the professor which was with me in the morning, he has also come back from NIH, one of my friends lab he has worked. So tuberculosis vaccine, and we feel because why we want to make the tuberculosis vaccine, because our honorable Prime Minister said that by 2025 we will like to eradicate the TB, and the only way to eradicate the disease is through vaccination. So let's see. I pray to God if we could succeed in our endeavor. So this is where we stand. But globally, what we want to say that Genoa should be able to create giga factories of mRNA, where we can supply billion people if the need would, create national and regional stockpile, do the technology transfer we are doing at present through the countries, and deployability. So this whole structure which we have created, we are moving into this direction. And then the most important part of this technology, why revolutionizing it, is that these are the raw materials you have kept in your warehouse. Only thing you have to change the sequence of the plasmid, which takes like 15 days, 20 days. And you have changed the plasmid and you can put into this funnel, because all the materials, all the manufacturing, all the analytics are exactly same, because just changing some basis of mRNA. So this is why this is a disease agnostic platform. You don't have to work on different products, different purification scheme, different bioreactor, different product characterization. No, it's all based on that. And finally, you mix with this, and the vaccine is ready. And that we have demonstrated by bringing two vaccines in the market. Just now, SAPI has come on the organization and they have given us a small funding, a few $1 million, and where we are going to use this platform as disease X platform. Because when you produce these things in the country, there are a lot of if and buts happens. So it is very important to go and muscle out the global market. That is very, very important. If you don't beat them into the competition, they will always see, there is some if and buts. So this is one of the certification we have. And now we have taken a challenge that can we create a vaccine in 100 days if need would be. So this is where the dream we are working, and this is the future path we're out there. Yes, there were some problems because our regulatory was not knowing what is mRNA. So first you have to explain to regulatory agencies what is mRNA, then they have to do this, and then I come from the scientific community, so business community has different ways and means, but I'm thankful to the government that they, any time if needed, I could have walked to the office of the Prime Minister, and that was the freedom was given to him. And this is the way the science is. Just like nuclear science, has been done because Bhabha was having opportunity to walk the Prime Minister's chamber without, and that should be given to our scientists. This is the only way our science can move forward, because this should not be fallen into the bureaucratic traps, because we are not bureaucrats, we have been trained as a scientist. So what we created a pandemic ready platform. We solved this problem of low temperature, and also we have solved the acute shortage of raw material. Next time we don't need it from anywhere. This is thank you slide, and just wanted to say, one of my colleague was last week in Berlin, and they were presenting next to each other. He was presenting this Project X on the Project X we have taken as a next generation rabies vaccine, because in last few years we are seeing the shortage globally of rabies vaccine, so we are making rabies vaccine. And she was presenting her work, so she came and appreciated her that this is I'm following Sanjay's work and your people work, how good you are doing. So we are at the same level. Not a question, we are at the same level. We just believe in ourselves and you can compete globally. That is what today India is. Thank you very much. Yes.
Congratulations for this success. But can you a little bit project that how mRNA vaccine is more useful than the protein vaccine or than the whole virus vaccine? Because why I'm asking, if you are using whole attenuated virus, you are having several, and against that our body will prepare vaccine. But when you are using mRNA, you are focusing on to single gene.
Thank you very much. This is a very important question. So when we were not versed with the technology, we were taking the whole virus and attenuating it and giving it as a vaccine. Yes, I agree with you that if you gave the whole virus, you have 2,000 antigens which antibody can be produced. But all 2,000s are not a protective one, because nature has evolved these things that if you get infected by flu this season, again next season you will be infected by flu. The correlates of protection are very important. This is one thing. On one side, there is advantage of 2,000 antigen, but there are a big disadvantage of 2,000 antigens, like dengue vaccine. If you have got the dengue, if the dengue vaccine been approved, and one of has not been approved in India in last couple of months, they tried, because there are certain antigens who create an environment where antibody dependent enhancement of disease happens. So hundreds and hundreds of children died when these vaccines were implemented in the case of dengue in Philippines and Indonesia. Yes, today also it is there, but we want to give the safest and most effective. So we define this is the particular immunogen is the most safest one. How to make immunogen? So we started making immunogen in terms of recombinant DNA technology, means recombinant protein, like HPV. There is the one protein. In case of hepatitis B, surface antigen, one protein. Because 99% correlation protection come from one or two proteins. So you can titrate and you can raise the level and you can give it to it. This is the one major question. Second question, can you imagine that which is killing our people, if we have to produce in 3,000 liter, grow the virus in 3,000 liter, how dangerous it is in the society? Anywhere where we are producing it, how dangerous it is, because we are growing the live virus and the people are there. And any calamities can produce another havoc. So this is, and it has happened. Case of FMD vaccine, even COVID. So that is another part. The third part comes the ease of manufacturing. So here you synthesize the DNA, put in your system, the vaccine is ready. You don't have to do thousands of liters of bioreactor. You can make in a test tube. So at present, we can produce 100 million doses in a 40 liter vessel. So this is the advantage of technology. So this is just taken to next. I have nothing against, because it has saved millions of lives. Like one example is polio vaccine. might have heard that few people got polio because of the polio, because it has not been attenuated. So government came and put very heavy restriction on that. So there are some out if and buts, but in going for the future, we want to safe and effective vaccine and which can be quickly deployable.
Thank you, sir, for your thought-provoking and excellent lecture. I, being a neurologist, I have two queries. I mean, this technology is currently being used for, say, vaccines. But when we talk of neurological diseases where there's a lot of neurodegenerative or heritodegenerative diseases that we come across, do you see this technology being used for those heritodegenerative or neurodegenerative diseases where you know the genetic mutation and you can program a messenger RNA, correct the mutation? Like few years back, we had this anti-oligonucleotide therapy being, they're still in the trials. The second use that the medicine can see is correcting the autoimmune diseases, because somehow we see autoimmune diseases where the body doesn't know when to fails to recognize self and starts producing antibodies against the self, right? And then this technology, if it can be used in those autoimmune diseases to correct the autoimmune process, that so that the body knows that this is own self and this is not a foreign body. So your comment on those two things, especially the heritodegenerative or the genetic diseases that we see, and those are a lot of spectrum in especially neurological diseases.
Yeah, thank you very much. So that would have taken my another hour. So we have a different program which is gene and cell therapy program. So at present, this area is known as by mRNA editing, and we are into it. Not in neurology, but at present we are in muscular dystrophy, and we are in one or two more things. This is science which is coming with mRNA, and I think few trials are going on in the neurology field. That is not a problem. I do not know if you're a neurologist. I was just talking to Professor Sukla. I'm very proud we have created the third generation politic, which is tenectage for single bolus for stroke. So this took us 13 years, two battles in the court. It costed more in the court than in the research, and but we succeeded it. If you are using it, so we are the winner of that. Yes, ease of being used. So now you see our trials, big results are coming. It is superior in a symptomatic intracorneal hemorrhage. Thank you. Yes. Yes. Need-based demand. And if vaccine cannot be deployed in India because it requires minus 70 degrees centigrade, it will be very, very difficult to transport it. So there was a need. There was, they never thought of there is a need. They never thought of there is a need to do this. It is just observation, and just if you say that lyophilization is very simple, yes, I agree, lyophilization is very simple. But it took us around 18,000 hours of more than 180 people 24/7 find the right condition, how to lyophilize mRNA to not break down. Create the whole cycle, create all the things. So it was not easy. It was very, very difficult because everything which gets lyophilized, it has a different parameters, have different, and then you have to maintain that same immunological response you are getting. So yes, it is very simple. Whole science is very simple. Science is a very, very simple thing, whether how you critically think about it. I agree with you. Very simple. Yeah, please.
Hello. I'm Rakesh and I'm working in the field of parasitology. I'm working on Lispania vaccines. But
So day before yesterday, my paper has come in Nature
oh
Communication
yes,
on
I
Lispania.
read. I got from Hira.
Okay.
I have collaboration with. I know you, sir. Really a blessing. I'm seeing you here right in front of me. My question is that I am observing immunologic tolerance if because I am not able to write the amount of antigen or immunogens in my vaccine preparations. As you said that you are using self-replicating mRNAs, and I think that self-replicating mRNAs may also may lead to such problem that the antigen don't have control over antigen quantity, how much, because that may lead to immunologic tolerance. How do you address this question?
Highly confidential and sensitive. These are trade information, but the kind of design of construct we have made and the machinery we have made, it produces antigen up to the same breadth up to 10 days, but between 10 to 25th days it die down to zero. And that data we are not going to publish. So, so that is that. So this is the way we have done this. And mRNA we were not working since COVID. We are working from 2017. And here we have titrated how to get the best immune response because we want the B cell get matured. And now BioNTech has just started another trial using self-amplifying mRNA. So it's a field was available for last 20 years. Only we have mastered it based on the need. So it is very, very important access these questions and answer these questions. And these are very simple questions. So we have worked on this. It took us around 1.5 years to different beam. So you can imagine for this presentation which I've given, around 350 people are in the company who work on the mRNA technology. Always. Thank you.
Thank you so much, sir. It was indeed enlightening. I know students have a lot of questions, but we have to move on. But before we move on, I would just like to request our director, sir. Our director, sir, please state our speaker.
Thank you. Thank you. Thank you, sir, for the invitation.
No words.
Nice of you.
Thank you. I will talk to you. Okay.
Thank you, sir. May I now request Head, Department of Chemistry, Professor Maya Singh, sir, please introduce the eminence of our last speaker.
Honorable dignitaries, distinguished speakers of the day, distinguished professors of Banaras Hindu University, my dear colleagues, students, ladies and gentlemen. To be very honest, Professor Hirendranath Ghosh doesn't need any introduction for the chemical sciences up to a certain age of the life. Since it's a mixed gathering, a brief introduction about Professor Hirendranath Ghosh I am going to share with you. Currently, Professor Ghosh is the director, Naishar Bhubaneswar. He earned his UG and PG BSc from Vishwabharati University, Shantiniketan,
followed by MSc from Indian Institute of Technology, Kharagpur. After that, he earned his PhD from University of Bombay, Mumbai, then pursued postdoctoral research from Emory University, Atlanta, USA, and after that, he joined Park Training School, where he served from 2000 to 2007. After that, he joined faculty in Homi Bhabha National Institute, Anuksha Nagar, and still he is continuing as a faculty there. After that, he became adjunct faculty of so many academic institutions. For example, currently he is adjunct faculty Savitri Phule University, Institute of Nanoscience and Technology, Mohali, and then Institute of Nanoscience and Technology, INST, Mohali. Over his past 23 years of academic and research experience, Professor Ghosh has guided 25 PhD students, 10 postdoctoral students, and more than 30 undergraduate and trainee students. His focused area of research is experimental physical chemistry and, in particular, ultra-fast spectroscopy. He has earned to his credit so many recognitions, awards, and honors of the chemical sciences. To be a very much brief and precise, he is fellow of all the three science academies of our country. He is J.C. Bose Fellows. He received the CRSI bronze and silver medal. Silver medal he received this last year in the year 2022. Apart from these branded chemical sciences recognition, he became the fellow of National Academy of Engineering, New Delhi in 2023. So over past more than 20 years of his academics and research career, he had over 240 research publications in the journals of high repute. Apart from the publications, he had contributed 7 book chapters, having citation more than 9,500 with H index 48. So with this brief outline, I would like to request for your talk.
Can you hear me? Thank you, Professor Singh, for introducing me and Professor Tripathi inviting me. It was a tough job when he invited me. I took the charge of director NISA just 6 weeks back, and I think your invitation came just 3 weeks back. I was really, trust me, I was a little reluctant to do that, but my entire career, I changed my title a little bit. New era in optoelectronics. My entire career, actually, I owe to quantum dots. That's the artificial atoms, people say. Three person got Nobel Prize, but actually many more people are involved. And if you see in my slides, I misplaced one slide, which is Matt Boundy, Mongi Boundy's slides. I just missed it. But what I'm trying to tell that these 3 person got Nobel Prize: Bawandi, Bruce, and Amikov, and Ekimov. Sorry, and this is basically artificial atoms. And my research work will be highly connected with this. So this talk will be heavily based on my own research work, because I followed all these people work from I think late last century, like from 95 or so, that I was doing something different. And I sort of make a correction Actually, after what Professor Singh, I joined Bhabha Atomic Research Center 1989 training school. And there I joined in chemistry department as scientific officer. And got, while you are officer, you get the PhD degree from DRC. Went to US, but I was always faculty there. Anyway, so this is basically artificial atoms, quantum dots. I just want to tell why you get Nobel Prize out of their work. If you read their initial papers, they did not get published in a top journal. That's normal. That's concept. That's what we talk about publishing paper, science, nature, and all this glossy journal. But trust me, major Nobel Prize comes from the simple thinking. But Professor our Nobel laureate C.V. Raman told it's a thought process, and you don't need to publish in a top journal. Many of my papers are cited by Nobel laureates, but I publish some normal journal of physics chemistry later. Mostly I publish there. So there are a lot of application in this material. That's why so much of attractive things has come. I can tell you some other things like it's a tunable chemistry. I'll come out of what material it is. Quantum dot, artificial atom, tunable chemistry. Then you have tunable states. It can make heterostructures, and then you can easily manufacture. Then there are lots of applications. Actually, I'm not going to tell all this. From bioimaging to medicine, drug delivery, energy harvesting, solar concentrator, then your illumination, display, cameras, charge transport, you get augmented reality, machine vision, communication, quantum information. All this, the new age technology, is the new age technology materials. That's why Nobel Prize was given. Okay. This is the seeds of nanoscience and nanotechnology. I mean, people are talking about a nano, but particularly the revolution came in solar energy. It came after making the quantum dots. So you have silicon solar cell, but the problem with the silicon solar cell, first thing that India missed the bus. I mean, in 1960s, India used to do a lot of research, but we missed the bus. We do not want to miss the bus in quantum dots. The main important factor for the quantum dots is in a silicon solar cell, your thickness of the material is a couple of 100 microns, like 200 microns. The material cost is very high. But if you make quantum dot thin film solar cell, the material cost come down, but the initial efficiency was very less. So that's why people are doing lots of research. Initially, Dyson solar cell. Then there are many things came, and finally quantum dot solar cell, where your thickness of the material is very less, and still you can get very high efficiency. That's why it's a very important material. It has also bioimaging. I mean, the medical application, drug delivery, LEDs. You can see the blue color LED. A couple of years before, Japanese scientists got the Nobel Prize for the colored LED. So all these materials actually you can generate from out of quantum dot by changing size and shape. And this is one of the most important that let me talk about catalysis, where you can generate hydrogen, indium phosphide quantum dots. There are many more quantum dots, and also heterostructure also people can generate hydrogen. Those are everywhere. The quantum confinement effect and the idea of confinement is very much important. This is very, very important. Infrared spectrometer. The infrared spectrometer or near infrared spectrometer, people use mercury cadmium telluride, MCT. Okay, it's a toxic carcinogenic materials, and it's very costly. This is going to bring us some. I don't know whether Nobel Prize will come or not, but simple zinc oxide from the defect state. Zinc oxide is very cheap from the defect states. To understand the science properly, actually you can make spectrometer about the very natural material which is non-toxic. All the knowledge is coming from a quantum dot. Yeah. So the best why this material has given Nobel Prize, the main reason is this energy material. That's what I talked. I've changed my title of the talk. Energy material, because you know that if you see this in India, how much is electricity generated? Majority is coal and some oil, also natural gas, and solar is still less, 16%. But eventually, if you avoid the greenhouse effect and the temperature of the earth, which is increasing, you have to rely on solar and nuclear. I'm from nuclear institute, that's why I'm telling nuclear. Also very important. But major solar material, what we are putting doing it actually. These are all silicon and coming from China. We have to generate our own material, and quantum dot actually can solve the problem. And that's what we are doing in this country. This photovoltaic performance is started from 70s, early 70s, and with time, new type of material come and you get the efficiency. The highest efficiency what we observed in the multi-junction solar cell, and you get around 48%, but it's a multiple junction, your cost effectivity is very high. I'll come to the point. You have to find a new cheap material where efficiency will be very good, at the same time it can be applicable. So there are two shaded region I'm explaining, not shaded the region. This is basically quantum dot material. You can see the curve. From 2010, people started making quantum dot solar cell. And the next is that perovskite quantum. That is also, the concept comes from quantum dot. That's why I'm trying to tell these two materials we are talking much. And finally, this is another material coming with tandem solar cell. Take the silicon, on top of it, perovskite quantum. It is coming almost 33%. It is more than the silicon solar cell, although the material cost should be much, much less. Okay, that's why the research in quantum dots is very, very important. Research on what it is, mechanism. That's I come. So my research is the entire last in 2 decades based on the synthesis of materials, ultrafast spectroscopy, and device application. Device application includes making of solar cell, and also for devices. So the game-changing strategy for clean energy, you can see that DSSC, that is dye-sensitive solar cell, 13%, and silicon is 26%. That's the ideal condition. Okay, and in ideal condition, this slide is actually a little older slide. Perovskite we have shown 5% and quantum dot 17%. But the latest, I think, couple of 1 or 2 months back, the report came from House, 33% with the perovskite on silicon. That's a process your silicon solar cell. Very thin layer is there, on top perovskite is there. And also, storage battery, when you have with these cells, you can make a clean energy. And another thing which I'm trying to tell you that from the normal mobile, you can the kind of device, everybody is having that. Those material color gamut has been changed drastically. You can have quantum dot AALG stuff. And also LED, there all kind of different colors if you generate. The quantum dot is a very cost effective and also very different color you can. What is the difference between LCD and QLED? You can see the number of different materials comes is way too high compared to the quantum dot LED. Both quantum dot TV and Samsung, actually both the LG and Samsung, they are making QD TV, and then that will be the highest resolution of color. I mean, it is already coming in the market. It is now the cost is higher, but eventually, what is the future perspective? That in Chandrayaan, we send this Chandrayaan things in space, and the solar cell actually have here. This is our basic active material multi. Very, very thick material, and also efficiency. It has a very high efficiency, but the thick material and weight of the material much higher, and the stability of the material also much, much less, particularly at the low temperature. The future of a device which the government of India is planning to send this quantum dot silicon perovskite quantum dot solar cell, where they are trying to see the temperature also, because that after one moon day it did not get up because materials has gone bad. That's why the battery did not work and the camera did not work, whatever reason. But what I'm trying to tell, people are doing research at low temperature when this material will go. Let's come to the history of quantum dots. Actually, history starts much earlier. Talk about the steel source which is made of carbon nanotube. So our ironsmith people, they did not know this. Actually, people say Alexander did not come for gold or silver. He wanted to get this metal, gold. And how they made it? When the ironsmiths are making the iron, they are making trying to make sword out of the coal and that the people was making carbon nanotube, and that's why have carbon nanotube and carbon and steel, making kind of steel, and it was very stable and it doesn't get rust and all kind of stuff. In addition to that, have Leica glass where you can see different color. These all properties actually coming from the confinement effect. The metal nanoparticle, all different color you guess from the plasmonic band, it's a confinement effect. Again, here even this carbon nanotube means really bulk. The nanotube is playing a role. The science of quantum dots actually exists much before. So what I'm trying to tell here, that the Indian, if you see the history of Indian craftsmen sword made with the carbon nanotube, that is ancient India, and then come Feynman 1959, he predicted that plenty of room at the bottom. That basically started off quantum concept, and then Kohn actually did a DFT calculation where he DFT calculation and Ekimov size dependent properties, and then in glass matrix group size effect in seed case, and also Bawandi, which is he talked about the DFT code, no, not about. This is the DFT code, and then early 90s, Bawandi hot injection method he did, where he synthesized all the cadmium sulfide selenide material, and then I am telling the from the ancient India to up to 98 how it came. Now, once this Bawandi work came, after that, because these are the materials you are using in solar cell, you are giving photon and you are creating exciton, and then exciton and bioexciton. This is a new type of physics understanding came to the picture, and these processes he understood up to picosecond phenomenon. And then Klimov ultrafast dynamics he started in 98, and I started ultrafast processes in early 2000. From there our journey started. You can see these 3% got Nobel Prize in 2003. Okay. So how is the work actually? It's a very simple work. It published in some Russian journal where they talked about the quantum size effect in three-dimensional conductor. They took copper chloride, they put in a crystal and made in different sizes and put some kind of a thin film and took the optical absorption spectra in the low temperature and figure out that as you decrease size, excitonic band, position excitonic band getting higher and higher energy. That is the first quantum effect experimentally described, size dependent. Then comes actually he is a theoretician, but this experiment he did, he took the cadmium sulfide crystal and he described the redox property quantum size effect. So when you have a semiconductors, a particular size, you excite, you create electron and hole, and then this electron certain place, it has some redox property, and oxygen, the hole has some oxidation property. As you change the size, the energy level of the conduction band goes up, the redox property of the electron is changing. Okay, and what you observe is Raman spectroscopy. It suggested that as you change the size, energy level changes, and that's create a big history. And next is that Bawandi, what he did here, synthesized cadmium sulfide, cadmium cellulide, and cadmium telluride. This is basically, I must tell, it's a game-changing thing. What he did, he made synthesized cadmium sulfide nanoparticles, and by some kind of synthetic method, I will tell, he could synthesize different size of nanoparticles, just different size. Okay, I mean by changing the reaction temperature and the precursor concentration. What you observe, he took one material and create multiple color. Here also there are three different materials there. But what I'm trying to tell that here you can see the optical absorption spectra, how it is changing. It can give blue color, it can give red color. with the same material actually. That's what I'm trying to understand. And that is basically game changer. So after that, theoretical calculation comes much stronger and understanding the subject comes much stronger. And people really realize that this is a material which can, because of the exciting property, the extension coefficient of the absorption light is very, very strong. It can absorb light very strongly, and it can generate current or electricity converts efficiency much better than even silicon and dye sensitive. Now let me talk about this quantum dot. It's basically a semiconductor nanocrystal, and if the size of the particle can bring down below Bohr radius, you can calculate Bohr radius through this. Size dependent dielectric constant. M is the mass of electron, mu is the reduced mass, and AB is the Bohr radius of hydrogen atom. You can calculate every material like cadmium sulfide, cellerite, telluride, or whatever has different Bohr radius. So if you suppose a cadmium selenide Bohr radius 6 nanometer, you calculate it. You can synthesize the cadmium selenide less than 6 nanometer, then you can start watching the quantization effect. So you can see as the size you are decreasing, the color emits from the particle red to the blue. So let's come here. Why I am telling that quantum dot is an artificial atom. You start with a molecule, and I'm sure many of you theoretical physicists or chemists, they might be working on clusters. Even experimental people are doing it. Gas phase people, they do clusters. So when many molecules come together, like 7 or 10 or 15, you make clusters. What is the effect of the cluster? The energy level. This is the LUMO, the HOMO. The levels of this energy level, LUMO and HOMO, actually decreases and add like more than 100 atoms, then you get the quantum dots. Okay, so this is absolutely new properties you get. You know, those who work in clusters, one atom makes so much of difference in your cluster properties. Now, coming to the quantum dot, if we talk about the artificial, so these are the confined states of the valence band, and this is the confined state of the conduction band. Now, this confinement effect, which is the 3 papers I was talking, it has been discovered and brings a lot of interesting property or interesting behavior of the material and lots of applications which I was talking. Now, those who studied valence band and conduction band in the bulk material, like say for bulk, if cadmium selenide is like 6 nanometer Bohr radius, anything above 6, maybe 10 or 50 or 100 nanometers material, it we say as the bulk semiconductors. What is bulk semiconductors? To excite the material, create hole in the valence band and electron in the conduction band. Okay, and if you give energy, for then your the energy band gap will be generated here and electron will be generated here. As the density of states of the conduction band is very, very high, relaxation process of the electron and the hole will be very, very fast. The electron emission will be very high. So, case of quantum dot, as the gap is higher and also states are confined. Okay, this property actually leads us to make a very interesting material for solar cell and other. Relaxation process of the electron will be much, much slow, and that electron what you generate in the quantum dot will be having high redox behavior compared to the semiconductor. If you make a quantum dot solar cell compared to the semiconductor solar cell, give a photon, the relaxation process in semiconductors or bulk will be faster. Okay, thermal electron, thermalized electron will be less effective for making solar efficiency, but in case of the electron is hot, back from it much, much better. So this is particularly in a box in quantum dots, the typical boundary condition. The energy level of the every state we talk about n square h square by m square. I'm taking all different confined states. How it happened? What is size quantization? I was telling that if you take a bulb, the energy gap is like a bulb band gap we tell. As you bring down the size, what we observe, the confined states basically gap between them is in, okay, and if you still further low, this gap is in, and also the confined state is released. And this looks like that. So energy of a band gap of a material can be easily calculated from this. This is the bulk band gap. Energy of any this quantum dot gap between, you have to calculate like this. Mass of electron, mass of hole, the radii, and this is a pi value. This is a typical example. It came in chemical physics, ChemPhys came. Cadmium selenide, they have synthesized a material very small to big size. And you can see the all colors you can observe. This color actually is a lot of implications. I told you why the color is different. Because the band gap is small, color emits between that maximum that band gap. If the band gap is more, color. That's why you observe. This is very, very important. I don't know, people who are doing photochemistry or chemistry, if you take a molecule, if you excite it, go to the upper excited states, and it starts from the ground state, okay? S1, S2, S2. Always transition takes place from the ground excited state. Say optical absorption spectra, something like that, and you tell S0 to S1, S2 to S0, and whatever you want to do. In case of semiconductor, things are very different. As I told you, I explained you, in case of bulk, the density of state is very high. These are kind of continuous. In case of semiconductor and nanocrystals, artificial atom we talk, the gap is much higher and there are different states. And the optical spectra what you take, it is not like always from 1s to 1sc or 1p. This is basically different kind of transition takes place. Take a cadmium selenide and take off this spectra. This one band is there, either there. This is cadmium sulfide, cadmium selenide. This kind of observation, the person who talked about the confinement effect, cadmium selenide, they never bothered. People like us who actually worked in this field and did ultrafast spectroscopy, they came into this phenomena. What we see that, like one is the transition from lowest confined state to the one electron, and one is this where a transition, and this is like a 1p and 3s, all kind of things are there. There, actually, this concept helps to grow the subject bigger and bigger, and multiple applications come to the typical synthesis, where all Matt Bowendy and Ali Visatos, everybody did this work. But with time, how the field actually modified and bring lot of important information, and that is basically application. So how we synthesize this material? As a chemist, I should tell you, like this is a typical precursor used, and with the same material, same reaction vessel, how to generate different side material. So start with the synthesis. It is some kind of coordinating solvent. Is a stabilizer. Surfactant is there, and then syringe add the precursor. Initially, if you got the concentration of the precursor, initially go and adding, it is increasing. Suddenly it can drop. The nucleation point actually started, and as you time goes on, you can see that particle sizes gradually. After a certain time, phosphor ripening, and all different kind of particles you can generate, cadmium sulfide, selenide, and different kind of optical properties you can observe. It looks like that. In a typical laboratory, you can see this kind of stuff. Telling much is a nitrogen here, gas, and then precursor, and the temperature. Here the temperature has to monitor. Now, how to arrest this? After suppose you want to work up to 10 seconds. After 10 seconds, you stop it, or not 10 seconds. 1 minute, a different way you can do. After 1 minute, you stop the reaction and put in the ice water. You can arrest the reaction. Particle size will not grow. The Bowendy 93 actually he published from this work. He got the the Nobel Prize work started. Later on, Elie Visatos also did a lot of work, and this, although we have started 2007 or 8, so very good particle size cadmium sulfide. So now my expertise come here actually. Make application of this material for mechanistic aspect is very, very important. Just by making the material doing some theory and telling this is not enough. When you excite the material, you create electron hole, and the cooling process, the relaxation process of the electron, and very, very important. Multiple process takes place, like phonon bottleneck, K recombination. You don't need to see all this. When, when, when the gap between these states are very high, and the phonon energy is like 80, 25 million electron volt. The gap is like 50 or 100 MeV. That case, phonon relaxation process will be very, very slow. That's called phonon bottleneck. Now, the cooling dynamics of a semiconductor is really slow when you go for lower side. But interestingly, what we observe, when you take the material, the cooling process is very fast, because in quantum dot, with the electron hole they go by, instead of cooling actually, there is a OJ recombination takes place. That OJ recombination give extra energy and give the electron to the energy to the hole, and again the cooling. This is something very, very interesting. And another thing I'll tell you, if the energy of the photon is very high, say for example, the band gap is 1 electron volt, and you give more than 2 electron volt energy, one photon, what it does, what create 1 electron hole pair. The energy of the electron is much higher. So what it does, it can extract 1 more electron from them. One photon can create more than 2 electrons. The energy of the photon 3 or 4 times can create even 3 electron hole pairs. So that's called multiple exciton generations, and your efficiency of the quantum dot solar rays can improve. These are the very interesting concept, and you really need to have ultra-fast spectrometer in all different regimes, which I did actually. I have developed in our atomic center. In between 5 years, I was in Mohali, and in all these places, the laboratory we did, and we tried to understand the mechanistic aspect of the electron and hole moving out. Okay, so for quantum dot solar cell, which is basically I did a lot of work, maybe till 7 or 8 years before, where talked about because we have to compete with the silicon solar cells, understanding the dynamics processes. The quantum dot, you excite it and you create electron. This electron has to go TiE2, that's basically electrode, FTO coated glass, and the hole has to be extracted, have some kind of electrode, and finally the electron goes here, the current comes this side. The processes actually takes place. Just now we gave a talk on attosecond pulse. This process also takes femtosecond. This kind of system actually we have built in the app, and this charge transfer is comes to the second or femtosecond, and carrier trapping. Carrier also trap. If you have defected, it gets trapped. And then also recombination time, nanosecond to millisecond. All these things you can see that. So this physics Nobel Prize, it came actually. To be honest, I started my ultrafast journey early 90s. From 93, we started making ultrafast lab in Bombay, and I think there we worked for 3 years without publishing the paper, but we learned a lot. What I was telling them, making all kind of laser spectrometer is very difficult. Somebody of you can come to my lab, even at the lab which I have now, managed to years. It's a big, big setup, and understanding these things is not easy. That's why attosecond pulse is very limited. Many people tried it, but it's very difficult in this country. So that's I'm not going. So the femtosecond thing is very, very important to make any devices. Understand? The quantum dot would never get Nobel Prize. The ultrafast spectroscopy tell that yes, this is the material. Why this material is important? Because there's a tremendous science in it, and those science we have unearthed. Now I'll talk about what is our contribution in my research. More than 15 students got PhD, and more than 10 people postdoc in this only quantum dot in my lab. So we talked about this quantum dot solar cell, which I was talking it, and what we found that the quantum dot solar cell we working, there is a limited efficiency. The reason are there. Because these are the different reasons I have talked about. Transfer, very fast exciton trapping state. come out this, we tried many systems. I don't want to really tell all this. From only quantum dot, another molecules, make a charge transfer complex, the absorption cross section changes, charge recombination is, and we found that the efficiency curve is much more improved. That's what we have shown, and these papers we published last month. This is also another quantum dot material, make a core shell, does ultrafast studies, and did all kind of devices and figure out actually things can be done. Most important thing in quantum dot solar cell was the whole transfer. The time scale actually nobody was able to tell how fast the whole transfer can take place. The system we have demonstrated how fast the whole transfer is take place. You can see this from the transient kinetics. Actually, you can talk of the whole transfer. Change your material in such a way you can extract the whole from the confined states and you can make a better device. These are the very interesting important. Take quantum dot, try to make some kind of device material. There's something called type 1 and type 2, I don't know. They were studying semiconductor physics. These are semiconductors, valence band and conduction band. Take another semiconductor. The band gap is higher. Say for example, cadmium sulfide, cadmium silicate, telluride. So cadmium sulfide is higher band gap, cadmium sulfide is higher. This is called type 1, type 2, and this is quasi type 2. You can make your material in such a way, you can make a higher efficient solar cell so that your electron can be delocalized and hole can be localized. The recombination process, which I was taking, combination with the electron hole, that played a big role. That can be slowed down by delocalizing the electron in two semiconductors conduction band. You have shown it. You can see that the efficiency is much higher. Basically, the concept, this concept eventually come and understand and try to modify it and get a bigger. Other example we did manganese doping also, and then heterostructure. This is very important. This heterostructure. So when you put a quantum dot in Ti2, for electron has to go. Now, as I was telling you, the recombination between electron hole takes place. Instead of that, if you put a gold nanoparticle, which can actually extract the electron from the semiconductor, we could see the higher efficiency. So cadmium, this lead, all this material, these are all carcinogenic. Many times asked that, also work with this copper indium sulfide, silver indium sulfide. Mind you, these are all quantum dot material. All kind of properties you studied. Published a paper in JPC Data Perspective, same as the perspective cover page article. So all these processes actually never knew, it is never reported in the literature. Now let's talk about the non-conventional quantum. The concept of quantum dot, artificial atom, for which the Nobel Prize was given, is not ends there actually. There are multiple Nobel Prize might come. The field has exploded, I'll tell you. Particularly a person like me, who is basically ultrafast spectroscopist and physical chemist, there are 4 different systems actually we are working currently, and where we have learned so much about the subject and the application. Mind it, again I'm trying to tell you, confinement. Perovskite, I'm sure many of you know what is perovskite. And also 3 materials, another important material. 3 material, the people gave the Nobel Prize for caffeine, but it's a zero band gap material for devices is very difficult. That's why people, monolayer, like MOS, they are behaving like semiconductors and the plasmonic materials and also heterojunction. All this concept comes from perovskite quantum dots. The advantage what you observe is the luminescence spectra of organic emitters and inorganic quantum. Perovskite is a very short, the bandwidth. Short bandwidth means for color resolution you will get much better. Same perovskite, you can change the, you can say the entire color gamut. Okay. This is a one curve we have shown. The quantum dot to the perovskite, the efficiency. That's the new material for quantum dot. Okay. quantum dots, perovskite quantum dots has a higher efficiency, and also the lifetime is higher, narrow bandwidth, and very easy to tune the band gap and energy. Again, I brought this card about this thing where we are suggesting that perovskite quantum dot suddenly is jumping like anything, and these cards actually basically perovskite and on top of it silicon. And another important thing I can tell you, I think in Tokyo 29 May, they have discovered that this is another application of the quantum. The perovskite quantum dot color gamut is 94% compared to earlier it was there 88%. 94% means the television screen, you can see the complete resolution of the color. Okay, so when we started working with the perovskite quantum dots and trying to understand how the efficiency can be improved, we started working on ultrafast spectroscopy, seeing laser pulse, excited, and try to find out how the carrier cooling can be. We came out something very interesting quasi-particle in the perovskites. Perovskite is the high polar material and the soft material. Excited, in the excited state, there is a movement among the vibration motion takes place in the perovskite material, and it can emit tons of phonon because of high polar. When the phonon is there in the material, the electron on the hole, they can be covered by the phonon, and you get to know polaron. Okay, polaron is a very important concept. We talked about the formation of polaron and decay of polaron, and lifetime and sizes in our work. It is very, very important to understand the making of efficient devices. We have also changed the structure, crystal structure, and figured out the polaron size can be increased or decreased, and also found out that if polaron size is bigger, the mobility of the electron is also down because it is a bigger shape, and that's what we have done it. And temperature dependent study figured out that if you can make it close to defect free materials, what you can do it, you can make a material where the carriers will be made of a higher polaronic size and the mobility of the carriers also. This is very important. Take a quantum dot, excite it. In one case, you have a defect, and in one case, you have a defect free. In where you have a defect free state, found that polaron formation is fast and a decay is slower. In this case, polaron decay. We did some terahertz studies, which is basically ultrafast studies, where we can talk about the mobility and the conductivity of the carriers. So without connecting these things, the device, terahertz studies, one can determine all this. That's what we did it, and this is also very. Finally, another thing we discussed about the confinement effect. You know that talk about the zero dimensional, but other than you have 3D and 1D. 3D material when I was talking, we make a material where confinement is taking place in one direction, other two directions is bulk. Then we excited both the material and figured out that in the case of 2D material, your polaron formation is not there. So the carriers, what happened? You excite it, the phonon emission is much, much faster. Because of that, polaron formation. This is something we discussed, that in case of materials, you have a faster relaxation and prodic interaction is strong. In this case, slower relaxation, and then that's why you have polar. So, in this case, you do not have polaron formation because your phonon is completely gone out of the system. Make polaron, electron is not, phonon is not there covered with that. And finally, the 2D material, again I was telling it, the confinement properties actually very, very important. And as I was telling that graphene is not a very good material for devices. For devices, people made MOS2, WS2, 3 material, where band gap is there. This band gap material can make it and you can use for devices, and this confinement effect in one direction and so on. So this I already discussed that in case of 2D, find that how the journey of 2D started. Then MOS2 you have 2010, 11 you get the transistors, electronics, the photodetectors, and here also very important, in case of 2D materials, when you excite the semiconducting material in a 2D surface, create electron and hole. Electron and hole, due to the Coulombic interaction, they form exciton. Okay, that's what generally you find exciton in case of 3D semiconductors or 0D semiconductor. But if it is a 2D, immediately you cannot make exciton because first you create free carriers, electron hole running around the 2D surface, and eventually, due to the Coulombic interaction, they will interact each other, they form exciton. There will be a time the surface, not only your exciton will be there, you have free carriers. Free carriers will interact, either electron or hole, interact with the exciton, can form positively charged exciton, that is positive charged trion and negative. This work actually we have demonstrated the negatively charged trion, where two electron and one hole interact, and in this case, and one electron. Typically, we have observed. So, let's talk about the future and what is the future of this. So far, Nobel Prize we gave it, and you have to make it a very high level and different kind of system. One of them is the telecommunication. You can use it where NIR light actually can be used. The expensive is very biocompatibility is very important. To use for biological application is very important. And the most important is that low temperature sustainability. The material what you synthesize, make, if at minus 200 temperature, if we cannot sustain, then the space application. So there are a lot of future and a lot of hope. And finally, I should acknowledge a lot of people who did PhD and now some of them are still doing it, and a lot of postdoc students. And the funding I got most from KRNS. I also work in INST. I am from HBNI Institute. And ACRB, I got a CRG fund and also JC was. All this fund actually help you to do the research. And finally, thank you for listening my talk.
Thank you so much. We may take these couple of questions now.
Yes. No. Decrease the gap, increase the gap. It become bulk. Yeah. Yeah. So here I talked about the polaron. You are talking about polaron stuff. What type of polaron can be formed? No. Phonon. Basically, these are all longitudinal phonon, yellow phonon. The time scale of the phonon is around 2. We are not bothering that dynamics. We are bothering it once of the electron is there, and when the loss of phonon is acting, and they make a cover of this electron. That's called polaron. But this phonons actually so lifetime of the polaron gets covered by that. During the short period of time, the mobility of the carrier actually decreases. So when you make a device, you don't know all this nitty-gritty of how the carriers behave, how the polarity is there, and all. You cannot make a higher efficient devices. Quantum confinement story is over. Now you have to make in the devices. We are doing all the research, get more efficient devices, whether it is solar cell or photodetectors or many things actually. Our research in transient studies in ultrafast, visible, near infrared, infrared, and terahertz, all different domain we work. We can unearth the story of all this. You take a solar cell and you really do not know. You make a material, you buy it. What is happening in this electron? What kind of quasi-particle generation? How to slow down all this? Like multiple exciton generations. Give one photon, get two electron, two. Now the problem is that because of the OJ recombination, two electron hole pair you might generate, but eventually one electron hole pair immediately recombine. They have a material which can extract the electron, all the hole from the, then only you can get higher devices. For these ultra-fast studies we are doing, they can recommend the extra energy they give. That extra energy, sometimes what is there, they pump up the hole in a higher state. They are doing process, but you end up with losing one electron hole pair which you have generated. If you can make a device, which we done it actually, the gold nanoparticle. Gold nanoparticle, the electron can be extracted in the plasmonic band of the, okay? It can go very fast. And the gold also connected to your devices. We have observed more than 2 times higher efficiency. Yeah.
Atoms. In what?
I told you, the starting from atoms is very LUMO and HOMO states. Why I am telling artificial atoms? Because you can manipulate its properties by changing size, by adding more number of atoms. That's why we call artificial atom. That's the main reason actually. You can see the optical properties, spectroscopic properties, all properties. You can do whatever you like. Like it takes a hydrogen atom or whatever, helium. You cannot change its properties. Make a material, you can manipulate its property the way you want. That's why you call artificial. SARS. Well, this quantum dot I do not know, but for the gold, we have seen that the SARS intensity is drastic. Anybody has studied this? Much higher, much higher. Gold, when particle size is very small, the SARS property increases drastically. Yes, I was telling you this, like solar cell, normal semiconductor solar cell efficiency is that. You cannot, ACRS means common spectroscopy, we are not bothered of the bothered of the solar cell. See, quantum dot, I'm not using there. I'm telling the SARS studies, I have never done it. I'm just giving an example. I've seen the size dependent SARS problem. I've never talked about the plasmonic. Semiconductor, quantum dot. Bulls are not quantum dots. They're plasmonic material. They're not quantum.
Thank you so much. I would now like to request our director, sir, and dean state. Felicitate the speaker. Knowledge shared is knowledge squared. With this note, I would like to finally thank the vendor of the lectures, the eminence today, Professor Dikshit, Professor Ghosh, and Professor Singh, their enlightening, powerful, and insightful presentations. With this, I would now like to request our Dean, Faculty of Science, for his comment.
So Tripathi, our director, distinguished speakers of the day, Senior Professor Maya Shankar Singh and other senior teachers of Professor Chalapati Rao, and dear students. This tradition of calling excellent people and celebrating science was started by our founder, Pandit Madan Mohan. Pandit Madan Mohan Malviya had also invited Sir C.V. Raman, PHU, speak to the students and the faculty. What do we get with such ventures? We not only celebrate science, we not only celebrate the excellence that has been achieved by various workers like the Nobel laureates, that is the highest award in various fields in which it is given. We also get inspiration of how such high award winning ideas were conceived by great people, how they were executed. Even if it was serendipity, how a thought came out of that which fetched Nobel Prize to them. And why students are encouraged to come here. They can get inspiration, they can see how scientific thoughts are built. And then tomorrow, as one of the speakers said, maybe one of the Nobel laureates be coming from. So I wish you all the best for that and my blessings for that. I thank Professor Tripathi and his entire team, particularly Professor Chelapati, being so meticulous in organizing it since the time he has taken over directorship. This event has become an integral part of the Institute of Science. So thank you very much for your leadership and qualities. And thanks to all the distinguished speakers. Just now spoke so well. And before him, Dr. Dikshit and Dr. Singh. See, Nobel Prize fetching scientific work is of a very, very high quality, which attracts the attention of laymen as well as professionals. It comes in the newspaper. Common people also read why Nobel Prize was, but they don't understand the basics of it. Even we as scientists do not understand all the. Today you have seen how experts belong to related areas have read their work and also shared their own work with you and made the things so easy. They have assimilated and then given the same thing in a very easy way that today we all understand why these 3 Nobel Prizes were given. Persons were there behind you. So thank you very much, sir, for giving me this opportunity to give a quick remark. And I hope that this tradition that has started. Thanks.
At last, I request Dr. Richa Arya, the member of the committee, kindly come here and cast.
Thank you, Archana. So it's an opportunity for me to recognize all who have immensely contributed and made event a success. So certainly, I would start thanking Vice Chancellor. He didn't come here, but he is always very encouraging and supportive. I then would like to thank our speakers, Pal Dikshit, H.N. Ghosh, for extending their time and knowledge to help us understand the scientific advancement that recently got recognition. I also want to thank our rector, sir, Professor Shukla, our director, Professor Anurag Tripathi, and our dean, SM Singh sir, for gracing the event and also conceptualizing the idea of this. I want to thank all the heads of the department, our faculty, and distinguished members for their support and cooperation in the event. Thanks are due the committee members, the Anvi Chalapatira, who is our coordinator, and he is organizing all these activities. Dr. Archana for anchoring, Dr. Akhtar Ali and Dr. Amia for all the support and also ensuring the smooth execution of this event. I would also like to thank our staff, especially at the Directorate Office and here at Mahamana Hall, especially Munnaji. He's staying very late, even yesterday, to get all the things functional so that we should not have any issues. And our volunteers are helping us live streaming, crafts, and all the other small activities which are is behind the scene may not be seen by many others, but without them, an event cannot be done. And I would also like to thank you all for joining us for this excellent scientific retreat. And finally, before we go for the high tea, which we all are waiting, I would like you all, I would like to request you all to please join us for the Rashtragan. विंध्य हिमाचल यमुना गंगा जल जल शुभ नामे जागे अब शुभ आशीष मांगे आए तब कण मंगलदायक जय हे भारत भाग्य जय हे जय हे जय हे जय जय. Thank you.